All right, ladies, gentlemen. Hopefully this is recording. I have no idea if it really is or not.
Good morning, ladies and gentlemen.
Good morning, ladies and gentlemen. The fact is, this microphone may be working, it may not be working, so this entire thing might be mute. So at least luckily you guys are here just to go over this with us today. So right now we're going to go over the practice exam, and we'll go over some of the harder questions. But if you guys have particular questions that you want to go over, that's fine as well. I only want to spend an hour on this, so if I don't get through the entire exam, I may ask you guys just to help me skip ahead. Okay? So for example, with the very first page, do I need to go over any questions on the very first page? Or can I skip the first page for the most part? Yeah? Good? Everyone understands what mistakes they made? Everyone understands that gravity only points down, right? It never points up. Don't confuse gravity with velocity. Okay, then let's just jump right to the second page.
Number 6.
All right, number 6. Okay, so for number 6, an object is dropped from rest. Now, if you remember, I told you guys on your note cards you should write down specific notes as to how to approach these kinds of questions. And the fact is, every question is going to look a little bit different. Key words here are height and kinetic energy. Well, usually when you think height and kinetic energy, and especially if it's dropped from rest, an object that's falling down, you think that at the top it has potential energy. Wherever it is falling down, it's turning into kinetic energy. So for the most part, all you guys have to understand is that potential energy is turning into kinetic energy. Really, the change in potential energy is turning into kinetic energy. Now, normally our approach is to turn these symbols, these variables, into the formulas. Like UG is really mgh. And normally I turn Ke equals to 1/2 mv squared, but do I really need to turn it to 1/2 mv squared in this case? No, because they're asking us to solve for kinetic energy. So you just set it equal to kinetic energy. The height, ultimately, is the distance d that's fallen. So in this case, what's kinetic energy directly proportional to? D.
It's that simple.
It's that simple, yes.
You don't include G?
Well, do any of our answers include G?
No,
Okay. In this case, it's asking about for each individual variable. It is directly proportional to gravity as well, but that's not what the question was asking. Okay. Number 7. Overall, is a pretty simple question, but it just have to be careful about. Okay. Be careful about the drawing itself. Okay. But this is potential energy and kinetic energy yet again. But the key difference is that it's being thrown vertically upward. So the ball is being thrown up. So we know, of course, at the same time that there's kinetic energy at the bottom and it's turning to gravitational potential energy at the top. So because of that, choice C would be incorrect. Well, halfway through, it does have half the potential energy as compared to the top. But initially, how much potential energy did it really have at the bottom? 0, which is why C is incorrect. Okay? Total mechanical energy is kinetic plus potential. For the most part, that always stays constant. Can't be D or E. So in this case, it can only be either A or B. Well, overall, we had just shown that kinetic energy is directly proportional to height and distance. So over here, you have half the height, so you have half the UG, half KE, ends up being choice B. The reason why it's not half the speed is because if we take a look at this as a multiplier question, well, kinetic energy equals to 1/2 mv squared. Okay? Half the kinetic energy does not mean the same thing as half the speed. In fact, if you wanted to have half the kinetic energy, if you turn it into a multiplier, 1 times 1 times 1 squared, it would need to be 1 times 1 times 1 over radical 2 squared. So the speed would need to be divided by radical 2, not by 2. So when you have speed divided by radical 2, you end up with half kinetic energy divided by 2. Number 8. I know a lot of people had trouble with. Initially, how much momentum was there in the system? Right? None. Because they were at rest. Okay? So in this case, whenever you have a collision question or they're separating apart, there's always conservation of momentum. Now, the fact is, right away, you should have looked at this and been able to say, well, the adult has a velocity of v. The child with a mass of m should have how much speed to cancel out the other one's momentum? It should be, Demi? 2v. Okay, so one's positive, one's negative. And so overall, the total momentum is still equal to 0. Okay, so right away, you should have known that. But they weren't asking about momentum, they're asking about work. So really, the real question is, what is work? Now remember, whenever you're working on something, ultimately, yes, working on something is done by force times distance, but that doesn't apply in this case. But when you're working on something, you're also changing its energy. In this case, what kind of energy are the people gaining? That's going to be, Hamza? It's going to be kinetic energy. So really, overall, you just have to say, how much kinetic energy is there after they push apart? So kinetic energy is 1/2 mv squared, so let's just add them up. 1/2 2m times v squared plus 1/2 m times 2v squared. Now the reason I'm adding is because this is a scalar quantity. Direction does not matter. Okay? Does anyone need an extra copy of the practice exam?
Because it's a scalar, you don't write -2v.
Right. Because it's scalar, I don't include direction signs. Okay, so overall, this becomes, if I just work this out, the 1/2 of 2, this becomes mv squared plus, now the 2v becomes 4v squared, because I square everything inside, so this becomes 2mv squared when I work it out, so the total is equal to 3mv squared. Okay, and I don't know what answer choice that was, but, okay. E. Choice E. Okay. Any questions about that? Okay. For number 9, I'm going to just talk about this quickly. The key word here is elastic collision. If you don't know what elastic means, you should write this down. But elastic means energy is conserved during the collision. And of course, because it is a collision, momentum is always conserved as well. If you have conservation of energy, conservation momentum, well, however much momentum there was before, P is equal to mv. However much kinetic energy there was before, 1/2 mv squared, that stays exactly the same before and after. So, this is choice A. Okay? Now, number 10 is an excellent question because this comes up very often on the AP. I told you guys that whenever you see a graph, the very first thing you have to do is write down what does slope equal to, what does area equal to, because that will give you a hint as to how to solve the problem. Now, slope in this case would be force divided by time, delta F over delta T. But do we have a formula for force over time? No. But what we do have is area, which equals to force times time, is the same thing as impulse, or change in momentum. So impulse, which is force times time, which is really F, sigma F times T, is also equal to the change in momentum. That's what impulse really means. I know impulse could be used with a letter J. I just never use J because to me, delta P explains it so much better. But overall, that means that if I solve for the entire area inside, that is equal to delta P. So overall, use color, 2 times 2, this is 2, 1 times 2. So overall, the total area is 4. When we do 4 equals m delta v, they're asking us what is the change in velocity. They gave us a mass over here. The answer delta v would just be 2 meters per second. Don't forget that an impulse can be positive or negative. Okay? If the force is being, in this case, it is positive because it is in the same direction of motion, meaning the object is moving to the right and there's a force being applied to the right as well. If the force or impulse were applied in the opposite direction, then it would be slowing down. Nadia?
Is the area of the middle one 4, not 2?
Oh,
That's right.
sorry. 4 divided by 2 in my head by accident. 6. So the delta v would be 3.
I did a getaway, but I still got the same answer. I saw for the acceleration in the middle, mass times acceleration, and I saw that accelerated for 2 seconds, and that would be 2 meters per second, and then so it was like half a second like each, so that equals 1, so it's like 3 meters per second.
Right, you can do it that way as well. But that's kind of what you did. Same, in a roundabout way. Okay. How much work is done during circular motion?
None.
Okay, easy. This is a very famous trick question. Make sure you memorize it because it's pretty often on the AP. But why is there no work being done? It's a better question. Why is there no work being done? Siddhant?
Because the motion is perpendicular to the force, not
Right, because the motion is perpendicular to the force. Good. 12. In this case, I know I went over period very briefly. In fact, I only did it really during the last review session. But if you know your formula for period of spring and period of pendulum, then technically they say they each have the same frequency, or same period really, because frequency is equal to 1 over period. But period of a spring is equal to 2 pi radical m over k. Period of a pendulum is equal to 2 pi radical L over G. So in this case, all we really have to do is set them equal to each other. 2 pi's cross out. The radical sign crosses out as well. So we're really left with m over k is equal to L over G. Okay. So overall, in this case, they're asking us what is the length of the pendulum. So when we just cross multiply, L is equal to mg over k. Any questions about that? Okay. In this case, it's really as simple as knowing what the formulas are for period. Yes, Vanessa?
What is the formula that's 1 over 2 pi?
frequency.
Thank you.
1 over 2 pi?
Yeah, one of the formulas is 1 over 2 pi instead.
1 over 4 pi. Yeah, which one?
You mean 1 over 4 pi epsilon naught?
Never mind.
The electrostatic constant is 1 over 4 pi.
No, it's 1 over 2 pi times radical on that. Isn't that the frequency of the?
Oh, you mean if you want just to flip the whole thing to solve for frequency? Yeah, you could do it that way also. So you could do 1 over. Okay, same thing. 13. A spherical planet has a mass greater than that of Earth, but its density is unknown. How do the weights compare? Well, the fact is, if you don't know the density, ultimately, what are they telling you that you don't know? You don't know its... well, they tell you the mass is greater already. But besides mass, Brian, you don't know its volume or its radius. Okay? So because its density is unknown, that means the volume is unknown, which is really the radius is unknown. So they're asking us, how does the weight compare? Well, what is the formula for weight in this case? Well, if we're talking about size of a planet, it's really Fg equals to G m1 m2 over r squared. So in this case, they said the mass of the planet is larger. So is the weight automatically larger as well? But in this case, it can't be, because if we don't know if the radius is larger, if it's a bigger planet or a smaller planet, we have no idea how it's going to compare. So overall, it cannot be determined without the Planck size, because we don't know the radius in order to complete our multiplier question. $14 and $15, I'm just going to skip because I thought they were pretty easy. 16. Okay. There you go. 16 is actually an easy question, but it's hard because you have to do math in your head. In 16, they ask us how much pressure is being applied. Well, this is actually a fluids forming where we have pressure is equal to force over area. Now they tell us that the force is 30 newtons. The question is, what's the area? They give us the radius, and it's probably a circular button if it's going to be a button. So area is, of course, pi r squared. Now I'm going to write it out in actual numbers. Well, I'll write pi r squared first. So pi is really 3.14. Now the radius, they say, is 1 centimeter. Now on your reference table, in case you don't remember, it tells you centimeter is 10 to the negative 2 meters squared. Now part of the reason I wrote this out is 3.14. Remember, this is all about estimation. So what's 30 divided by 3.14 really, approximately? 10, right? So we'll just cross it out, write that as 10. Okay? So now, but what's 10 to the negative 2 squared? Now, whenever you square exponents, you multiply the exponents. So this is really becomes 10 divided by 10 to the negative 4. And whenever you divide exponents, you subtract them. So 10 to the first minus negative 4 becomes 10 to the fifth. Any questions? Okay, so like I said, this was hard only because you have to do some mental math. But remember, it's all about estimation and about canceling things out. All right, fluids. A ball that can float on water has a mass of 5 kilograms and a volume of 2.5 times 10 to the negative 2. They ask how much downward force must be applied to the ball to hold it motionless. So the key word here is, of course, motionless, meaning that all the forces are balanced. So let's just draw a quick free body diagram here. We know buoyant force points up, mg points down, and the force that you're looking for points down as well. And because it's balanced, what formula should I automatically be able to write based on my free body diagram? If it's all balanced, what should I automatically be able to write? Maria? So FB is equal to F plus mg. Everything up equals everything down. So the force is really equal to FB minus mg. So overall, we already know mg. That's easy. That's 50. But what's FB? In this case, you just have to remember that FB, the formula is rho Vg, based on the density of the fluid. So it's 1,000 times 2.5 times 10 to the negative 2.
Would the G's cancel?
No, you don't cancel the G's. Times 10 minus the 50 newtons for the weight. So in this case over here, you just have to say, well, what does this really multiply out to? So you just have to be able to, hopefully understand how exponents work. This is really 10 to a third, 10 to the first, 10 to the fourth. You get basically get 250. Minus the 50 newtons. So your total force is 200 newtons. But again, this is a very, very common type of fluids question, so please make sure that you take notes on it and you understand it. Okay. So water flows through the pipe as shown above. So you guys automatically, of course, should know that it's going to go faster where it's narrower, and it should be less pressure where it's narrower. Now this question doesn't pertain to that, of course. It's not asking us to do that directly, but I just want you guys to understand. You should be able to just look at it and be able to tell. Okay, so, oh, by the way, for those of you who came in, there are bagels if you'd like, and there are drinks also. So in this case, the formula really is A1V1 equals A2V2. It's about flow rate. And they're asking us, what's the speed of the water at the other end, V2? Okay. Now, that means we simply need to turn the areas into the proper form because this is a circular pipe. It's really pi R1 squared V1 equals pi R2 squared V2. Pi is crossed out. Now, notice, however, they gave us diameter and not radius. But I want you guys to understand that, well, if you double the diameter, technically you're doubling the radius also, right? So it's still proportional. Even though we have radius here, if I had substituted it with diameter instead, honestly, there'd be absolutely no difference because because diameter divided by 2, on both sides will simply cancel out. So if you have the diameters already, one shortcut is that you don't have to use the radius. You could just use diameters on both sides. So really my final answer is, if I just do V2 is equal to V1 d squared over little d squared, which is choice E. Any questions about that? Robin? Well, it's pi r squared. Right? Area is pi r squared, so it's just pi times r squared. But instead of using radius, I use diameter. And that's circumference. Okay? So, just be careful about mistakes like that. Okay, 19 is a thermodynamics question. And it's about thermal expansion here. And the formula for thermal expansion is delta L is equal to alpha L naught delta T. In other words, the change in length, coefficient of thermal expansion, times the original length, times the change in temperature. The key thing here is that the change in length is directly related to change in temperature. So they tell us that when there's a change in temperature of 8 degrees Celsius, delta L is 0.4. But if the temperature of the floor were to decrease from 20 degrees to 8 degrees Celsius, now there's a delta T, and even though it's a negative delta T, or of negative 12 degrees, it's going to be directly proportional to that. How much is it going to shrink by now? Well, it increased by 50%, so it's still going to be, it'll shrink by 0.6 centimeters. Okay? So even though we don't know what alpha is, nor do we know what the original length is, it doesn't matter. Because as long as you remember that the change in length is directly proportional to change in temperature, it works out. Temperature is directly proportional to average kinetic energy. This kinetic energy equals to 3/2 kBT, for number 20. Okay, I'm just going to skip right past that. 21. So if you knew, for 20, if you knew the formula, you automatically knew the answer. But most of you hopefully knew that temperature is directly related to kinetic energy already anyway. Now overall though, in this question, we have a lot of numbers here. We have some temperatures and some energies. But the key word that's important is the maximum possible work. Because whenever they talk about maximum efficiency, or ideal efficiency, or Carnot efficiency, that's Carnot, which is TH minus TC over TH. Hot minus cold over hot. This is still thermodynamics, yes. But they're saying that this heat engine is an ideal engine. And because it is an ideal engine, we can also, this Carnot efficiency is the same thing as the real efficiency. So we can set this equal to work over QH. So you end up with 700 Kelvin. Make sure it's in Kelvin, by the way. Divide by 700, which is really 3/7. Because 300 over 700 is 3/7. Is equal to work over QH. They're asking us for what's work over 2,800 joules. Now, in this case, it actually would have been easier. If I had left this as 300 over 700, you would see that it's a direct ratio. This got 4 times bigger on the bottom, so therefore it has to get 4 times bigger on the top also. Okay, 4 times 400 basically. And the answer ends up being 1,200 joules. Any questions? Okay. Okay. For 22 and 23, let's just look at this little diagram over here. They ask what's the electric potential at the center and what's the electric field at the center. Okay. Well, electric potential is simply KQ over R. And the great thing about electric potential is that it's scalar. Okay? So whenever we talk about electric potential, it's scalar. So all you have to do is just add them all up. We don't care about direction. So in terms of sigma V, it just ends up being, for the first one, KQ over R plus KQ over R plus K2Q over R plus KQ over R. So really 1 plus 1 plus 2 plus 1 is equal to 4KQ over R. This is the only 5KQ over I meant, sorry. This is the only formula though that you have to include charge signs for. Okay? So if any of these were negative, you just insert the negative in and they just cancel each other out. Okay, so we have to include charge signs. Now, if we're talking about electric field, however, electric field in this formula is not on your reference table, but you have to understand it's a combination of other formulas. But you should know your formula is E equals KQ over R squared. And it goes out of positive in each case. So for the first one, it's going, at point P, it's going down right. But that cancels out with this one over here, which is going up left. They're balanced. Overall, the bottom left one is going upright, but this one is twice the charge, so it's going to be twice as powerful, not balanced. We can see they're going to subtract from each other because they're going opposite directions. So technically, when you have 2KQ over R squared minus 1KQ over R squared, because they're going opposite directions, you end up with 1KQ over R squared as your final answer. Any questions about that? Okay. Hopefully this is all recorded, so you always can review these notes. If you didn't understand that, we'll see if it actually worked or not. All right, 24. Okay. Now 24, we're going into electrostatics now. We have two spheres, X and Y. Now, X is uncharged, and Y has a charge Q. And the two of them touch. So the question is, now remember, the charge is only on the surface. You should make a note of that. Charge only on surface. And in general, but with any sort of sphere, the electric field in the middle is equal to 0. This has nothing to do with the problem, but just notes it for yourselves. But the question is, when the two of them touch each other, how much charge is going to go over? Now, this has a charge of 1, 2, 3, 4, 5, 6, 7, 8, -8 coulombs. How much charge is going to go over? Now, they're equally sized. It'd be easy, because then it'd just be equal. -4, -4. They just share the charge equally. Because it's not equally sized, Now remember, if I put 4 here and 4 here, it'd be a lot more crowded on the smaller one and a lot more spaced out on the larger one. But they all want to have the same spacing. So in the end, only a couple of charges might go over, and these will just space out a little bit more. Okay, but overall you might end up with -6 and -2, but then this way we have an equal spacing between all the charges. Now this is not equal distribution of charge, but it's an equal electric potential. Okay, potential of course means how much, I guess, electric height there is, or how much negative electric height in this case. Now they have the same potential because they have the same distribution of negative charge. They have the same overall negative height, you could say. Okay, so the answer is choice B. So they can't have the same charge, and we don't know if they're going to have half the charge because technically, even though it has twice the diameter, it's volume-wise is 4/3 pi r cubed, so that doesn't work out. Okay, so the only thing that makes sense here is choice B. 25 is a great capacitor question because this actually involves a ton of formulas and you understanding a lot of the formulas. So this will be a great review. They tell us that the distance is increased. They ask us what also increases. Well, let's go through each formula. Capacitance. C is equal to epsilon naught A over D. So if the distance increases, we can see that the capacitance decreases. So it's not A. Choice C, force or attraction between plates. Well, between two charges. And this formula does not exactly work for this scenario because it only works with point charges. But I'll deal with it, use it anyway. Fe equals to K Q1 Q2 over R squared, or really D squared. If I increase the distance between the plates, you can see the force decreases again. Can't be C. Electric field in the region between the plates. Well, you should automatically know whenever you have parallel plates, this is your parallel plate formula. E equals V over D. Distance increases, electric field can't be E. Okay. Now, yes.
What else is the field equal to?
What else is the electric field equal to?
Yeah.
I mean, you have the formula KQ over R squared, but that's only to be used for point charges, like what we were doing before. Okay. In the previous question, for E equals KQ over R squared, when you have individual charges creating an electric field, then that's going to be the case. Or you have E equals F over Q, which also is true, but that's talking about the force on a charge inside an electric field. This formula tells us if we have parallel plates, how much electric field those parallel plates are making. Anyway, the key word here really is isolated. Because if it's isolated, it means it's separated from the battery. Right? We had those battery attached to these parallel plates, which charged up the parallel plates. But once you isolate it, you remove the battery. What's the most important fact to remember once you remove the battery? Vanessa?
Charge in the plates doesn't change.
Right. The charge has nowhere to go. So that means Q is constant, which means it can't be choice D either, because the charge can't change if it's isolated. Now, of course, this leaves us with our default answer of B, electrostatic energy, but why is that the choice? Well, based on the formula, C is equal to Q over V. We're already proved that the capacitance is decreasing. If Q stays the same, that means that the potential difference must be increasing in order for that to work. So the potential difference would have been a possible choice of something that's increasing. However, also UC, the energy in a capacitor, is equal to 1/2 QV. Q stays the same, V goes up, energy goes up as well. So this was actually a very complicated answer for a simple question. Okay, but it gives us a good review of all the formulas. Capacitance based on size of the plates and distance between the plates, and the electric field created by parallel plates. Okay. So this has several questions attached to it. Okay, so understand here, we have all these switches attached. And they ask, in the first one, which one produces the greatest power dissipation in R2? So if you want the greatest power, that partially means that you have to have the greatest current, right? Going through. Well, which one obviously has to be closed in order for this to be true? Danish?
Switch 1.
If switch 1 isn't closed, you're not going to have any electricity go through any of the circuit at all. That's an obvious choice. Okay? And obviously, of course, switch 2 has to close also. Because if it didn't close, then no current will flow through R2. But the question is, what about switch 3? Okay? And I want you guys to understand, this wire over here is what I call a short circuit. Now, why is it called a short circuit? Well, basically, a short circuit is basically something that when a short circuit occurs, everything else turns off. Let's talk about why. Okay? Normally, when current flows through, when it reaches this junction, what's it going to do? It's going to split, right? Some will go here, some will go here, and some will go there. Okay. Now, which branch would receive the most current? Normally, which branch would receive the most current? Vanessa? Why do you say R2?
Because when it gets to the next junction, it's going to split up and then it's going to have less.
Well, technically, that's true, but that doesn't mean it has to give the most. You're right, some of it splits off, but if this was, let's say, 10 over here, right, going in, and only 1 went through R2, then the rest of it that's going would be 9. So it doesn't have to be R2, okay? But it does split off first into R2. In this case, the one that receives the most current would be Nick? I have no idea what you said. Brian?
R1.
R1, yes, you're right. R1 will receive the most current. That's before it splits. But I'm talking about between the 3 branches, which one receives the most current. Because, well, Sudan, since there's almost no resistance, okay? If there's almost no resistance here, low resistance, it's automatically going to get high current. In fact, the resistance is so low, it actually steals all the current from the other branches. That's what happens in a short circuit, because the battery can only provide current at a certain rate. Okay, it can't give it out at an infinite rate. So whenever a short circuit occurs, okay, the resistance is so low. So if I were to connect switch 3, resistor 2 and 3 would automatically turn off, because it would not get any more current. It would get so low current because the middle branch stole all of it in order to work. So the answer to 26 is choice C. You only want to close switch 1 and switch 2. You do not want to close switch 3 because that would cause a short circuit. But if they ask which one creates the greatest reading on the ammeter, you'd only want switch 1 and switch 3 because you want to avoid the other resistance. You want the most current. So 27 is choice E. 28. Which ones will produce the greatest voltage across resistor 3? Well, in this case, the answer would be switch 1. Because voltage means it's using up some of the energy, but you want it to have a higher resistance to get more of the energy. Yes?
What does dissipation mean?
Power dissipation simply means
Spreading out.
okay, dissipation simply means it's used up. Okay, so greatest power rate of use rate, something like that. So it's just a fancy word, just saying calculate the power. But overall, in 28, okay, you guys have to remember that in a series circuit, the voltage is proportional to the resistance. So if this was 10 volts, no, actually, if this was 12 volts, and this was 8 ohms and 4 ohms, then this one would get 8 volts, and this one would get 4 volts. The size of the resistor is proportional to the size of the voltage it claims. So overall, we want the resistance to be as large as possible, so you want to ignore the parallel circuit, and you only close switch 1. So that's the answer for 28. 29. Two cables can be used to wire a circuit. Cable A has lower resistivity. Well, first of all, what formula are they asking us to talk about? We're talking about resistivity. We're talking about R is equal to rho L over A. So cable A has a lower resistivity, a larger diameter, and a different length than cable B. Which cable should be used to minimize heat loss? They're really asking, when they say minimize heat loss, they want the lowest resistance possible. Well, the fact is, we can't tell. Because even though resistivity went down and area went up, do we know what happened to the length? No. So we can't tell what happened to resistance without knowing the length of the cable. Okay. Great question, the classic magnetism question. We have a current carrying wire carrying it this way, to the right. And if I were to ask you what's the direction of the magnetic field created by the wire, which hand rule should we use?
Right.
Not the left hand. We're not talking about the electron yet. We're just talking about the wire. Nick? The first hand rule. Okay? So with the first hand rule, the first thing you should do whenever you see a wire, Kim, how are you doing over there on your phone over here after you just come to extra help? I'm glad you're paying attention. So hopefully you guys can see it's going, the magnetic field is going into the page on one side and out of the page on the other side. So that means everywhere this is going into the page from the wire. But if I wanted to figure out, what's wrong, Vanessa?
I thought that if it was an electron, use your electron.
You do. We're not talking about the electron. Ignore the electron. Pretend it's not even there. The wire itself.
Yeah.
We always talk about,
Use your right hand.
always use your right hand with wires. We always talk about conventional current. Now when we look at the electron though, okay, now we're looking for the force on the electron. That's our left hand. So, everyone should be holding up their hand, thinking about this. The electron's going up the page, but the magnetic field's going into the page. So therefore, the force is going to the right. Okay. Now, in this case, how much force does it feel, though? Oh, FV is equal to QVB. But if you take a look at the question, that's none of our choices. But we also know that B is equal to mu naught I over 2 pi r times the QV. So therefore, you can see, if you know your formulas, then you can automatically see mu naught I over 2 pi r over Q times QV. So that would be choice A.
Hey.
Okay? So 30 is E, 31 is A.
I did this question right, but I just didn't think. I forgot which it was taught. That's okay. I just did this like so tired. I was like, morning, SSA.
Good morning, Matt. Whew. Again, if you guys would like to go get some food, go ahead, go get some food. Two wire loops lie in the same plane. The current in the outer loop is clockwise. So I'll just draw that. They've already drew it for us, but I'll just emphasize it. And increasing in time. Okay. So because the current... Now, right now, what I'm going to do is I'm going to draw the magnetic field of this outer loop. It goes like this to the left of the bottom. So when I use my first hand rule, I can see that's going overall into the page. Are you guys okay with that? Now, but as the current gets stronger, because the magnetic field is equal to mu naught I over 2 pi r, as the current gets stronger, the magnetic field gets stronger. So overall, what this is telling us is that the inward flux is increasing. It's getting stronger and stronger. So the question is, what is the other loop going to do? Well, the other loop, of course, is therefore going to try to weaken it. So the loop, the inside loop, makes an out of the page magnetic field to respond. So it looks like this. So it makes its own magnetic field out of the page to respond. And when it makes it out of the page, if you use your first hand rule again, with your fingers pointing out of the page, you can see that overall it's making a counterclockwise current. And this is choice C.
It can only make it inside of it.
It can only make what inside of it?
Like you see.
For this loop, the red X's, you mean? Well, on the outside, it would just be dots.
Yeah, but I'm confused as to, you know, the inner circle, their X is on the outside, so why wouldn't like the circle on the outside cancel it?
Okay, well, this outside loop is making X's everywhere inside itself. Okay? This inside loop, for the most part, is going to respond with what's changing on the inside. It also responds on the outside a little bit, but really what's changing on the inside. And on the inside of the loop, we can see that the into the field is getting stronger, into the page is getting stronger and stronger, which is why that inside loop will make an outward field to respond.
But on the outside, they would both be together, and they'd be like both out of
Yes.
the page, right?
Yes. Well, yes, you're right. This question we had on the test already. You guys just have to remember that EMF is equal to change in flux over time, change in B times A over T. And when they gave you the rate, that 3 Teslas is junk information because delta B over T is 0.5. Okay, that's for 33. All right, 34, let's look at the waves. Actually, this is too easy. I'm just going to point out. Amplitude is how high it is from the middle. That's 4 centimeters. What's the speed of the wave? That one's a better question.
Yeah, I didn't.
Are you guys calculating yourselves right now? Well, a couple things I'll point out. They tell us that the period is 0.2 seconds. So therefore, the frequency is equal to 1 over 0.2, which is 5 hertz. The wavelength is 1 crest, 1 trough, so it's therefore 10 centimeters. So therefore, V is equal to F lambda, which is in this case 50 centimeters per second. But I do want to point out that rather than using V equals F lambda, you guys could have simply done distance divided by time as well. Lambda divided by T is really the distance divided by time, which also works. Okay? Because frequency is the same thing as 1 over T.
The frequency equals V over wavelength.
Yes.
I have a question. When you're doing amplitude, you don't do it of both the top and the bottom, you just do it of middle to top and bottom.
That's amplitude. What's true for both sound waves and electromagnetic waves? The answer is everything. They're both waves. The only difference, the main difference between sound waves and electromagnetic waves is that one is longitudinal, one is transverse. I'll write this down for you guys, actually. Sound waves are longitudinal and mechanical waves. When I say they're mechanical, it means that they need a medium to travel through. That's why I don't hear sound in outer space. Electromagnetic waves, like light, is transverse and, well, they're electromagnetic waves, can travel in a vacuum. Okay? But one other extremely big difference between the two of them is that the energy of a mechanical wave is equal to its amplitude, meaning the larger the sound wave, the bigger the amplitude, or the larger the water wave, the bigger the amplitude. But for light, in our last unit, we understood that energy is based on frequency for light. Okay? So those are our main differences. Otherwise, they're both waves. They both act like waves, which is why the answer is choice E. Okay. Understand that the greater the difference in index of refractions, the greater the bend. So right now, in this case over here, for example, if red light was n is equal to 1.6 for red light inside the prism, for the violet light, n would equal to 1.66. If you're talking about from air, n equals 1. So you can see violet simply bends more because there's a greater difference from 1 to 1.66 versus 1 to 1.6. And the fact is, the higher the index of refraction, the slower it goes, the more it bends. So red light is choice B. Is faster in glass than violet light. Yes.
Can you say something is faster because it has a greater slope of the line?
Rather, you should say that,
The angle?
especially if you look over at this picture over here, which we'll go over this in a moment. But the main thing is that the angle is directly related to the speed. So, for example, when it goes from glass into ice, should it be getting faster or slower?
Glass into ice.
1.5 to 1.3. It should be getting, no, faster, because it's less dense. And if it's getting faster, that means the angle should be getting bigger. The speed and angle and wavelength are all directly related. So if this is measured from the normal line, it should look more like this with a larger angle. Okay, so you can't base it off of slope because it depends on how the whole thing might be rotated, you know. By rotated, the angle looks different, the slope looks different. Okay, but rather you have to take it from where the normal line is. Okay, double slit diffraction. Let's draw this. A wave hits. You know, at the other screen, you know, we have the bright spots and our dark spots. Okay, and it looks like if I want to do an intensity graph. Okay, the fact is, the reason we get this pattern is simply because of constructive and destructive interference. So if you have less light going through, you have less constructive and less destructive interference. You'll still have the same pattern, but it's just not going to interfere as much. And because it's not going to interfere as much, the answer is choice E. Dark lines are brighter, bright lines are darker.
Did you say they both can be darker?
No, I said it's not going to interfere as much, meaning that your graph will look more like the bright line isn't as bright, the dark line isn't as dark. Okay, so if less light going through, it's just not going to interfere as much. Okay, in this case, 39, I can use it on the previous one over here. Okay, we can see as it goes from glass into ice, the angle of refraction is larger, speeds up. Angle of reflection should be same. Okay, nice and easy. Reflection is always at the same angle. Okay, in this case over here, you can do this several different ways. Easiest way in my mind is to draw it. But if you're terrible at drawing, well, that's what practice is for. Parallel, then through F. Now the reason this is a little hard to draw, but if you have a straight edge, like your edge of your booklet, it's fine. You should see it looks like they're not going to meet. I know I'm slanting off, but I'm just... Okay. Or you could simply imagine, of course, that if you are looking at a converging lens, what's an example of a converging lens? Well, it's a convex lens, but I'm saying an example would be a magnifying glass.
What about the security mirror? Is that the concave?
That's a convex mirror. But in this case, a magnifying glass, when you look at something really close, it should appear larger, right? If you're holding the magnifying glass really up close to something, it should appear larger. Now, is it going to be upright or inverted? If you look through it, it'll be upright. If it's upright, that means it automatically has to be virtual as well. So anyway, in this case over here, we could do this with math as well. The focal length and point P, so we could have done this with math using 1 over di equals to plus 1 over dou equals to 1 over f. 1 over di is equal to 1 over 0.4, I think, was it? Yeah, 0.4 minus 1 over 0.3. Okay, in this case, you just subtract them out. 3 over 1.2 minus 4 over 1.2 equals to negative 1 over 1.2. So di is equal to negative 1.2 meters or centimeters or whatever it was. Okay. So in this case over here, the answer would be 1.2 to the left. Choice A, and it's also virtual, upright, and larger. Choice D. Yes.
When you get a negative, that means it's
Virtual.
Real total.
42 is a ridiculously easy question. They ask what's threshold frequency. If you knew that, you knew the answer. There you go. All right. 43 is actually a hard question because I didn't really teach the second part of the question. Now, 43, you should be able to take a good guess, though. Even if you don't know the answer, because of the second part, I taught you the first part. We have one red, one green. How does the energy of red versus green compare? Which one has a higher frequency? Which one has higher energy? Demi?
red has a lower frequency.
So therefore, red has lower energy. Okay. So right away, you should have been able to see it's not D, it's not E. Okay. Now the second part I didn't really teach you guys because I never really taught you guys about lasers. But the fact is, because they have the same intensity, overall the same total energy is for red and so there's the same total energy for red and for green. Even though individually each red has less energy, that means in order for the red to have the same energy as green, okay, there has to be more photons crossing per unit area. Okay, because if lasers have the same intensity, they're asking about, they're saying the same total energy is the same. But since there's less energy for each red, there has to be more of them to equal the green. So the answer is E. "44. You should know this one yourself. You should take a look when you look at it. So, oh, that's, you guys can see what's missing. 4-2, right? So if 4-2 is missing, that's going to be an alpha particle, which is a helium nucleus. Yes.
You know when you showed us the image where when you shine the red light, like photons just didn't come out? Does that depend on what you're shining? Like what?
You're talking about the work function with photoelectric effect?
It was
Okay.
like when you change the light color and then the photons didn't come out until you got to the green.
The electrons didn't come out.
Oh.
Because when I changed the photons, they just turned from red to orange to yellow to green. But when they're striking the photoelectric surface, they didn't come out until it reached green, because that surface had a threshold frequency of green, of whatever green light is.
Depends on what surface you're hitting?
Exactly.
And for that, the intensity only affects the kinetic energy of
No, the intensity is the number of photons you're shooting in. So if you shoot more photons in, you knock more electrons out. But they don't have any more energy. They have very little. So if you shoot one photon in, and it comes out with barely any energy, and if you shoot 100 photons in, they have 100 electrons that come out with barely any energy.
And so the kinetic energy is based on
The frequency of light.
The photon.
Right. Basically, how much energy you're shooting in. Like with the bowling ball, if I have given more kinetic energy, but making it go faster, it knocks the pin down with a greater speed. Okay. 45 is a units question.
Yeah, that's not great. That was weird. So what?
The units of any two quantities must be the same whenever they are added or subtracted.
Not how we're guessing.
Hopefully you guys knew that one. If you did not, I'm sorry. But if you multiply numbers, then the units just combine together. They just join together. But whenever you're adding or subtracting, it's just like 1x plus 2x equals 3x. But can you do 1x plus 2y? No. Can you do 1x times 2y? Then it just becomes 2xy, right? But in this case, 45 is... Anyway. 46 is a trick question. It's actually a common trick question. Keyword here is echo. That means the sound was given off. So it traveled, and then bounced and traveled back. Meaning, the actual distance away is based on a time of 0.3 seconds. The speed of sound is 340 meters per second. So distance usually goes to v times t. You guys can just take your best guess.
Yeah.
Now, by the way, can you guys do this in your head? 340 times 0.3?
It's 3 seconds.
Oh, 3. So I get for reading these things wrong. 340 times 3. All right, you guys should see it's about 1,020. Am I going too slow for you guys, or is this okay? 47 makes it sound complicated, but it's really a very simple question. You have two charged particles pushing against each other. They repel each other. One has a mass of m, the other has a mass of 2m. So if the particle x is going at That's crazy, I know. 2.2 meters per second squared. What should the acceleration of the particle y be? If it's double the mass, half the acceleration. Wrong one. Okay. Choice C. An object initially at rest is okay. They're asking us which one will exhibit a straight line relationship. This is actually what we did at the very beginning of the year when we talked about linearization. But to make this a little easier, all you really have to do is just look at the formula. Now, what is the formula that relates speed and distance of something that's acceleration? So they were v squared equals VO squared, which crosses out because it's at rest, is equal to 2AD. Or in this case, x minus x naught. Right, you're right. But in this case, it was just 2AD. That's what exhibits a straight line relationship. All you have to do is relate v squared versus d. That's a straight line relationship. But do we have v squared versus d? Oh, actually, we do.
Yeah.
Because I was going to square root both sides, but I don't have to. I was doing v versus the square root of d. 49 is a conservation momentum question. Key thing to write down and remember. X and Y axes, bless you, are separate. In fact, how much momentum is there on the y-axis before the collision? 0. So how much momentum should there be on the y-axis after it explodes apart or collision? None. So the only one that's impossible will be choice B. Because B has two things going down, which means that the momentums aren't canceling out. 50 is torque. I'll teach torque after we go through this packet. It's a super easy question. 51. Two charged spheres have the same amount of electric field just outside their surface. But how is the charge on X compared with that of charge on Y? Just outside this. So okay. Let's just go through the basics of this real quick first. What's the formula for electric field? KQ over R squared. Now, normally when we deal with the formula E equals KQ over R squared, we're dealing with point charges, right? So let's say that has a Q of whatever, then we can figure out the electric field at whatever point there is. Easy enough, at a certain distance away. But when you're dealing with a larger sphere, okay, you still measure all distances from the center, meaning that even though this is a sphere here, it has a certain charge, so over here I would measure the distance from the center to that location. Over here I measure, if I want to find the electric field at that location right there, you always measure from the center. Even though the electric field inside is 0, you always measure from the center. And this was actually an AP question one year. Now they're saying that they have the same E at the surfaces. They're saying that the E here they're saying that the E over here is equal to the E over here. Is it possible for them to have the same charge? The answer is no, it can't be. It can't be, because overall it's KQ1 over R1 squared equals E to KQ2 over R2 squared. We can see R1 is greater than R2. That make sense? So therefore, Q1, must be greater than Q2 in order for this to actually work out. So the answer is choice A. It has to be greater in order to get the same E equals KQ over R squared. You guys still want to continue with this packet? Or do you guys want to start something else like torque?
Yeah.
Work.
How many people want me to do torque?
None people want
Okay. How many people want me to finish the rest of the multiple choice? Okay. How many people actually did the multiple choice?
How many people attempted? I attempted.
How many people failed the multiple choice?
Yeah, we did it. We did it.
All right. Let me finish 52, 53, only because this was a test question, but I'll just mention it again.
Almost a good
And then we'll stop for now and talk about torque.
Can we take a 5-minute break? 5-minute break.
Sure, maybe we'll take a small break as well. They ask, solve for the total capacitance. Well, what do you remember? You combine series by doing what? How do you combine series capacitors, not resistors? Like parallel resistors, you're right, which means what? 1 over. So that's 1 over 3 plus 1 over 6. That becomes 2 over 6, which is really 3 over 6. But is 1 half the answer? No, because that's 1 over capacitors in series. So that total amount is equal to 2 microfarads. How do I combine capacitors in parallel? Like resistors in series, which means that I just add them. So the capacitors in parallel, 2 plus 2 is equal to 4. Now, for the next part, they ask us about the charge or the voltage, something like that. How does the charge and voltage compare across the two series ones? Okay. Now, in series circuits with resistors, what stays the same? What letter is in series that's not in parallel?
Charge is the same.
Well, charge is the same, but normally in resistors, current stays the same. Okay, I stays the same. In capacitors, since there is no more current, we have Q instead. For both parallel capacitors and resistors, V is the same, but for series, we have either current or charge. We know Q3 is equal to Q6. That's just automatically true. So you should have been able to automatically eliminate choices and take your best guess. But the question is, how do the voltages compare? Well, take a look at this. C is equal to Q over V. We know they have the same charge. So V is equal to Q over C. So if I take the same charge, Q divided by 3 versus Q divided by 6, you can see that this one has the larger voltage. So the answer to this one would be choice C.
So do you have any more, like, is there
Multiple choice,
like full length exam?
including part 2s.
Yeah.
Well, I put 2004, 2009 Schoology.
I
Okay.
looked it up and they said the quiz was.
Yeah, it said it wasn't available or something last night.
Okay, I'll just make it available. Sorry about that. But otherwise, for the part 2s, you can just find the part 2 by yourself. I just typed in 2004 Physics B free response. The reason I didn't upload those is because those are readily available to you.
Yeah.
Okay. But something like this practice exam isn't readily available to you guys. Okay.
So
Anyway.
it was all the ones you had, right?
Yeah. All right. Should I just do? No, I won't. I'll stop. All right, we'll take a 5-minute break and then I'll talk about torque.
Now we're getting it.
Let's go play ball out.
Yo, can we go play ball after this?
Let's just say, let's all play basketball.
Yo, let's go play ball. Oh my god. Yes. Yes, yes, yes.
Yo, Kim, can you make your sesame bagel, alright? Cream cheese. Sesame and seed bagel.
Why doesn't Vera do it herself?
Let's do my kid work.
It's working because Jeff heard. I woke up, right? And I watched your video like automatically. And I heard Theo come in and he said, someone some food? I'm like, there's food! And I came in right away.
So wait, are they still
So
listening?
it's working right now?
Are they still listening?
The quality is really good.
Wait,
Yeah.
they can still hear, but they can't see us?
No, that's yes.
I can't see you. I see the board.
Hello?
I hear some background, but it's mostly you.
Is anybody there? I love you.
What's up?
They're probably listening right now.
Great.
Somewhere over the rainbow.
That's real talk.
That's real talk, boy. Yo, I'm gonna rap to you guys right now. Let's go. Let's.
Another question, but there are a lot of formulas for Connecticut.
No,
Can you
there's
say
only one
some of them? What happened?
You guys want to do a playing ball
There
after?
are-
A billion types of energy? Yeah.
That's about.
You want to go? Get your ball. Where do you use your ball?
I'm over it.
Let's just look at Carbonaro.
1/2 kx squared equals 1/2 mv squared mgh.
Do you have another copy of that packet that we just did?
Go up, Barrett. Danny, are you gonna put the ball after?
Can I write on it?
Yeah, sure. I'll just give my shoes on. Let's go.
Yo, we're going with Drake. Drake, you should ball this.
Yeah.
Better than a what I've seen.
If you would like a second bagel, just go help yourselves. I didn't order too many.
I've been doing so many bagels this week. So many
I think it's
bagels.
for thermodynamics. This one. You said that one at the time?
That's how we get the formula. That's also the reference table.
Yeah, I didn't know what that meant.
It's the same formation.
No, but what is the RN master?
Average root mean square. Because this is really average kinetic energy. So we find that using it just means average velocity. Right? Of the average kinetic energy. Those gas molecules.
Of like many or just one?
I knew they weren't.
Don't worry, I'm the best cook.
Yeah.
Oh, they're getting money.
Is lit? Is lit?
Are you really pouring that on?
This is how you get the most money.
Do you want a monkey?
Oh.
Making the most money. Eventually you're gonna be driving the
Well, so you shot Vera. That's Vera. Where's Dylan?
He was here before.
Wait, how'd you discover this?
Yeah.
Like that?
I'll probably check it.
Don't tell
No, I was just wondering.
And then if you want to go through
Sorry, I practiced.
Now we're
It's 2 in the
getting
morning
it.
because I got there early. Yeah, I got there early.
This tomfoolery.
Here, what do you want here?
Time is it? Then there are FBI investigations.
Welcome to Physics Radio FM at 9 o'clock in the morning. This is your host Brian Carvajal bringing the latest physics to you.
What up, what up? Wait, is it actually like talking? Can people hear me right now?
Probably.
Is it on?
Yes.
Talk back if you can hear me. No.
He muted
I
everybody.
know that. Wait. I want to click on that thing.
I'm not designing. You make the design.
There's something about girl. Oh, Hamza, come on. There's something about girl makes my head wanna twirl.
All right. Back to Torque.
Is that guy?
Yeah. Next time I'll hook up the camera so we could all dance for them or something. Oh my. Do you guys want me to finish this later? Or I don't have to? Alright, we'll go through specific questions. Or is it really useless because you guys didn't really do a lot of it and then it's just...
I just want to learn something.
You just want to learn stuff?
Yeah.
Alright. You're not learning something when we go over this stuff?
No.
Okay.
It's too late for me.
Okay, bless you. Now, torque is a rotational force. Okay. The base formula is really tau is equal to R times F. I'll get to it, don't worry. So, for example, if we took a bird's eye view of a door. So here's the hinge. Here's the doorknob. Okay. Ultimately, okay, whenever you have something that is on an axis, okay, has some sort of central axis. In this case, the central axis, of course, is located where the doorknob is, where the hinges are. When I apply a force of, let's say, 10 newtons, and overall the door, it has a width of 1 meter, 0.5 meters. It's a small door. Okay. We can see that I'm producing, this is R is equal to that. The torque, amount of torque I'm producing is equal to R times F, which is equal to 0.5 meters times 10 newtons, or really 5 newton meters. Now, newton meters happen to be the unit of work as well, because work equals force times distance. And force times distance, newton meters, was the same thing as joules or energy. But this is not energy. Okay, so the unit is still 5 newton meters. And if you think about how doorknob is designed, have you ever thought about it's always placed as far as possible from the hinge? Because if I wanted to open a door, ultimately it's easiest when I'm pushing near the edge. If I was pushing in the middle, it takes a lot more force to produce the same amount of torque. If I have half the radius, what does that mean about the amount of force needed then? Not just, so in this case, if I want, right now it says 5 newton meters, right? If I'm applying 5 newton meters at the edge where the doorknob is, if I have half the distance now, how much force do I have to apply?
More.
Now, how much more?
Double.
Double. Half the distance, double the amount of force. Over here. Okay.
Stop.
It's actually really hard to open a door if you push near the hinge. Okay? Because if you have a very small, in fact, if I go all the way onto the hinge, would I really be able to push with enough force to rotate it? No, because if R is equal to 0, if you're on the hinge and you push on the hinge, okay, depending on where that force is, I produce different amounts of torque. Ultimately, if I push over here where the hinge is, I produce 0 torque. And over here, I produce the maximum amount of torque. Okay, does that make sense?
Is that why when you play baseball, you hit the bat at the end?
That's part of the reason. You don't hit it at the very end, though. But you do hit it near the end. And part of the reason you don't hit it at the end of the bat is because the bat, well, this is more about waves. A bat is actually a standing wave. When you hit a baseball with a bat, it actually vibrates like a standing wave. Do you guys in baseball understand something called a sweet spot?
Yeah.
Okay.
Softball, you gotta represent
Or softball, you have the sweet spot. When you're playing softball or baseball, when you hit it on the sweet spot, do you really feel it in your hands? No. That's because where you think about the standing wave is, right? You know how nodes and antinodes? If you hit it on exactly where the node is, that's the sweet spot. So where that sweet spot, that's a node. But if you go past the sweet spot, okay, it hurts. Because whenever you hit something not on the node, but more near the antinode, then you end up hitting something that creates a lot of vibrations in the entire system, which is why your hand feels it a lot. So whenever you hit it perfectly, you never feel it on the bat. Okay? And yes, you create more torque technically when you're rotating it near the end. So in the end, that's part of the reason why we do that. Yes?
What else does it apply to?
Almost everything. Well, I'm going to talk about this in a moment, but other examples I'll happily talk about are like a steering wheel in the car. If you think about a steering wheel in a car, and just when you're holding onto a steering wheel, okay, this looks terrible, but when a person holds onto a steering wheel, okay, the fact is, the reason you have a bigger steering wheel and not a smaller one is because the bigger it is, overall we have our radius here and the force that's being applied to turn the wheel. Okay? If you ever look at trucks, trucks have really big steering wheels. And part of the reason they have really big steering wheels is because it's a lot harder to turn a truck, because there's a lot more friction involved to turn the wheels. So part of the reason you have a big wheel is by applying the same force with a larger radius, you create more torque. That's one example. Okay. Another example is a basic screwdriver. If you think about a screwdriver, every screwdriver has a handle. Okay. So let me draw this out. I'll draw this out from two different points of view. I'll draw a side view. Okay, whatever. And then I'm going to draw a straight-on view.
That is a good screwdriver.
Okay. Now in this case, this is just I'm looking at the back of the screwdriver. When you take a screwdriver, and whenever you screw things in and out, ultimately the best screwdrivers, or the ones that are easiest to use, have a larger, thicker handle. Because a thicker handle means you have a greater radius to apply your force onto. So there's a radius, there's a force. Okay? Now, the thing is, the way a screwdriver works is that the amount of torque here is equal to the amount of torque there. The thing is, with a screwdriver, you have a large radius, you're applying a small force. But at the end, you have a small radius, but it's a large amount of force. And that's how a screwdriver works. Because the torques are equal, but they just have different radii at different points. Okay? But because they're both rotating at the same rate, they have to have the same amount of torque. How's this for? Are these good examples? Great. But technically, anything you rotate, even a hammer, right? A hammer, this is like a baseball bat, right? Okay. Okay, so with a hammer, it's partially, in this case, it's more about rotational velocity rather than torque itself. Okay, but in the end, anything that you're rotating, you're generating a torque force onto. Okay. All right. Now the thing is, with torque, and the formula, as I said, is torque is equal to, I'll do FR, or RF, doesn't really matter, same thing. But the thing is, the key difference versus work equals force times distance is that with work, the force must be parallel to the distance. But with torque, the force must be perpendicular with the radius. Think about that, right? So here's my door, here's my radius, if I push with a force parallel to the radius, is it really going to rotate at all? No. So whenever it's not perpendicular, you have to find the perpendicular component. Does that make sense?
Yeah.
Okay. So whenever it's not perpendicular, you have to find the perpendicular component. So let's actually do one quick practice question with a steering wheel. Okay. Your two hands, for some reason, decide to work. Now, by the way, sorry, before I forget, torque is also a vector. But we don't talk about left and right, up and down with torque. We talk about clockwise or counterclockwise. Okay? So overall, here, I might be grabbing the steering wheel with one hand. I can't draw that at all. Thumb and fingers grabbing on. Okay. Now the radius of the steering wheel, let's say, is 15 centimeters. And my hand applies a force in this direction of 50 newtons. For some reason, my brain gets crossed, and my other hand, over here, thumb, fingers, good enough, is applying a force in this direction of 50 newtons also. But this is at an angle of 30 degrees. So two forces are actually kind of look the same. But this one happens to be perfectly perpendicular. This one is not. You guys can see that? Okay. So right now, solve for torque 1, solve for torque 2. What's the total torque? Okay. So ultimately it's F1R1 plus F2R2. But be careful of the angle and be careful of the units. Vera, why are you sitting all the way over there?
Because I was eating.
You look like you're done eating.
No, not yet.
Now my first question to you is, are the two torques working with each other or against each other? Against each other. Torque 1 is going clockwise, right? And torque 2 is going counterclockwise. So you guys just have to make sure, for example, that you understand. So clockwise might be positive, counterclockwise might be negative. Okay? So when I write that torque 1 plus torque 2, it's really plus negative torque 2, because it's going in the opposite direction.
Wait, how are they going in the opposite direction? Aren't they both going that way?
Well, the two forces are but look at the wheel. Which way is this one rotating the wheel?
That way?
Which means clockwise or counterclockwise?
Clockwise.
And this one's rotating it.
But that force is going that way.
I don't care. Which way is the wheel rotating?
I don't know.
It gets. So which way is it rotating it? First of all, do we care about that component?
No.
No, because it's not perpendicular to the radius. We care about this component right over here, because it's perpendicular to the radius. So in this case over here, it goes counterclockwise. Exactly.
So is that like?
So it would be 50 newtons times 0.15 meters plus really negative 50 newtons times cosine 30 times 0.15 meters. So they don't cancel out perfectly. But you guys can see that this one's rotating clockwise, this one's rotating counterclockwise. The component we care about is the component that's perpendicular to the radius. So we end up with 7.5 minus, let's see, what was it? 6.49. So we end up with about 1 Newton meter clockwise. In fact, if we take a look at this question. Okay. The bathroom is open on the second floor, definitely. The teacher's lounge is definitely open. Okay? Guys, if you go into the teacher's lounge, though, please don't poke around looking in different corners and refrigerators and stuff. Because I've had instances in previous years where students thought, oh, look, there's free soda in the fridge. They kept it and put it in their lockers. So, yeah, I know.
Isn't there a vending machine in there?
There's a vending machine in there as well. Let's do this torque question right now. This is number 50 in your practice exam. A meter stick of negligible mass is placed on a fulcrum. At the 0.6 mark. Now, fulcrum is just like that triangle before I showed you guys. It's as if I place that meter stick on my finger and it's just rotating around the finger. So this is where the axis of rotation is. They place a 1 kilogram mass over here. Oh, no, they place a 2 kilogram mass there. The 1 kilogram mass is placed over here. And the 2 kilogram mass is placed over here. They ask, what's the net torque? Now, understand that 2 kilogram mass is going to be rotating it this way, and the 1 kilogram mass is rotating it this way. Okay? So this one ends up doing counterclockwise. This one ends up trying to make it clockwise. How are you guys with that right now? Can you guys envision that okay?
Yes.
Yeah.
Okay? So basically, if it's rotating around this one point, this is pulling it down, this is pulling it down that way. So if I drew as a big circle, you guys can see that this one's going counterclockwise, this one's going clockwise. So overall, we understand in this case, the force, of course, is the weight, M1G, M2G, and we can see that the radii, R1, R2, is simply based on the length of the meter stick. Solve for the total torque.
It doesn't want to follow, but it has to. The lighter one is let's say the heavier one. Yeah. That's how it makes sense.
Yes. Well, what's the weight? How much weight is literally pulling down on the edge of the ruler? What? So over here it'd be 20 newtons of pulling down, right, on one side. And over here it's 10 newtons pulling down. And that force is already perpendicular to the radius. Yeah. No. Because the force of tension would be within the free body diagram of the block. But we don't care about what's happening in the block. We're literally asking about what's happening at the edge of the ruler instead. We understand that ruler is being pulled down. Now, technically, guys, there's a third force. I drew two of the forces, but there's one more force in here. Technically, there's a third force, but in this case, it doesn't matter. Simply because it says that the ruler has negligible mass. Because otherwise, the third force would be right in the center, would be the weight of the ruler itself. Okay? But do we care about the weight of the ruler right now? No. So you guys just have to be careful about that idea, though. But because it's a negligible mass, I just care about the two ends. So I get 12 minus 4, which is equal to 8, counterclockwise. Any questions about that? Fatima?
How'd you get the 10 times the 0.4?
10 times 0.4.
Doesn't it say 1?
1 what? 1 kilogram? Which is 10 newtons?
No, it's 1. Yeah.
The 1 meter mark, but how far is that 1 meter mark from the axis of rotation? Thank you. It's only 0.4 meters away, which is why I drew R2 on the diagram from here, not as the entire meter stick. Liz. This one's counterclockwise. That one's clockwise. Are they going opposite rotations? Right. Okay. Now, the only other real type of torque question that you guys might see is something similar to that one over here. I'll draw the meter stick again, but really, rather than the meter stick, I'll deal with a seesaw. Now, assuming that this might be a, 5 meter long seesaw, we have a child sitting on the one end of the seesaw. He's a skinny one. He's just holding on. Okay? And that child, he's holding on, has a mass of maybe 50 kilograms. He looks like what? Anyway. He's holding on to the handle. Now, the other side has a larger child.
What's his name? I thought that was his name.
Okay? And he has a mass of, let's just say 100 kilograms. Now, the thing is, normally in this seesaw, as it's drawn, is it balanced? No, we can see this is not balanced torque. In fact, the larger child will probably lift up the smaller child, right? Yeah. But is there a way to make it balanced?
Yeah. No.
Yes. How could you make this situation balanced? So that way the torque on one side is equal to the torque on the other side. Vanessa? The bigger one can move in. So the problem is, we don't know how far in he needs to move. But we know he is going to move in. So your job is to figure out right now, where should he sit? Relative to the fulcrum, where should the larger child sit? Okay. We see R1. That's easy. Question is, where does the larger child sit? R2. Well, it doesn't matter which one's R1, R2. It's up to you. But where does the larger child have to sit in order so that the two torques are perfectly balanced? Because remember, torque is force and radius. So if he has too much force, you take away some of his radius to have the same torque.
Should just have to work.
We don't know if R2 is half of R1. Or whichever one's R2, R1's up to you. But the fulcrum is placed right in the middle. So R1 would be half of the 5 meters, yes. The blue radius is half the left. He's 100 kilograms, not 150.
They just said 150.
Oh yeah. But it doesn't work that way. Because it should be inversely related. When you do the proportion, it's directly related.
Wait, would it just be that?
Do you like physics Jeopardy, Mr. C?
Wait,
Do you like physics Jeopardy?
No, I don't like Physics Jeopardy. So that's the question.
I was gonna say, does it matter what the place is?
I don't know where the red person is placed. I only know the blue kid is at the end.
So,
Find the meters.
no, so he's placed at 5 meters.
No, he's not placed at 5 meters. How far is he from the fulcrum? Okay, that's his distance.
Close, Brian.
What's wrong?
I'm thinking that now yes, got it.
We know the two torques have to balance.
Okay, that's. Okay, I figured out.
Check yourself.
Give me 1 second.
It was really hard.
Aren't all AP
I got a lot.
Good.
Like a lot.
Good.
Like
Can I cry about it?
I didn't think
All right, guys. Shh. So hopefully you guys understand that because sigma torque is equal to 0, that means torque 1 minus torque 2 equals 0, which is why I set them equal to each other. And ultimately, you guys found that with twice the weight, he has to have half the distance, correct?
Seesaw has a handle. How can the bike get like pass it? You know what I'm saying? Seesaws have those handles. You said
You
yes
can
and
sit
no.
on the bar.
So how does he hold
You
on?
can sit wherever you want in a seesaw.
Maybe that.
He's a large child. I'm sure he'll manage. Jordani. Okay. All right. Shh. Okay. So, do you guys want one more example of this question? Or are you guys good now? And that's torque. Okay? All right. Now we can open it up to whatever questions you guys want. And I can go over specific topics if you guys would like to as well. And I write here thermodynamics. I can help you guys with the no part for thermodynamics. But before I just do a unit, any specific questions with regards to the AP packet? AP multiple choice.
Number 6 on the section.
Okay, number 6 on part 2s. Okay.
This is neat.
Okay, so in your practice exam, number 6. I'll go over number 6 quickly. key words here is they give us the wavelength of light is 520 nanometers, and they give us each of the indices of refraction. First of all, because this is keyword light, what should you automatically know if you know that's light? Automatically. Thank you for raising your hand, Brian.
Good job, man.
The speed of light, V or equals C, is 3 times 10 to the 8th meters per second. That's automatically given. So the wavelength is 520 nanometers. Nanos on your reference table is 10 to the -9. How do I solve for frequency? So V is equal to F lambda. So we end up with frequency equals 5.77 times 10 to the 14th hertz. And one of the things you should have written down on your Waves note card, if you made a Waves note card, is that frequency always stays the same during refraction. So 1 and 2 have the exact same answer. It's that simple.
Wait, can you say that again? Frequency always stays the same in what?
During refraction.
I got that, but I didn't get part of this. A3.
Wavelength, speed, and angle are all directly related and all change. Now, for wavelength, you have 2 ways to solve for part C. For part 3, the easiest, N1 lambda 1 equals N2
I
lambda 2.
forgot that's a thing.
This is not on your reference table, though. Otherwise, you could have solved it by using V is equal to F lambda again. You know the frequency, you're looking for wavelength, but the problem is it the same speed? No. So we'll have to use N is equal to C over V to solve for the speed first, and then use V equals F lambda. Or you could use N1 lambda 1 equals N2 lambda 2, like I told you to. Both work. Okay. Part B was the hard question. And this is something I spent some time with you guys on, but I know it's still hard to understand.
Intensity?
They asked us, calculate the minimum thickness of the oil film. Well, actually, can someone give me the lambda 2 first of all? What's the new wavelength? Just give it to me in nanometers. Or do you want me to do it myself? Because you guys are 371.43. Everyone got that? Yes, no? 525 divided by 1.4. 375. I got 375 nanometers. Is that what other people got? Yes, no? You guys are terrible and lazy. You're asking me to go over this. You guys could, at least do is do it with me. So lambda 2 equals 375 nanometers. Okay. Now, they're asking us at what thickness is it the most intense? Key word here is most intense, which means constructive interference. I told you, the answer is always going to be either half a wavelength or a quarter wavelength. This is our job to figure out which one it is. So, let's figure it out. I'll draw my layers. N equals 1, N equals 1.4, and then 1.5. Okay. Now, if you guys vaguely recall me going over this a long time ago, when light hits, okay, it always partially reflects, partially refracts. But in this case, whenever it goes into a denser medium, so right now, light goes in, let's say it's at 0 degrees. I don't know why I did square sign there. If it's at 0 degrees, it balances off, it partially goes through, and partially reflects. Partial reflection, partial refraction. The thing is, if it goes into a denser medium, Vera, then the fact is, in this case, it's going to reflect back upside down. In this case, 180 degrees. Okay, so whenever you're going into a denser medium, it always reflects back upside down. Now, we say that this thickness is half a wavelength. That means from 0, by the time it reaches the other side, half a wavelength, it's traveled 180 degrees. Because that's the wavelength. One full wavelength is 360. Now it goes through again. Partial reflection, partial refraction. It goes through at 180. But it reflects because it's going into a denser medium again. I'm going to do this in a different color here. It reflects back. So 180 plus 180 at 360. And by the time it travels all the way over there, well, 360, of course, is one whole wave. So if I say 360, you guys understand that's the same thing as 0 degrees? Yeah. Okay. Now if it's traveled another half wavelength, that means it's reached the other side back at 180. So when it comes out, it's 180. So 180, they're both at 180 degrees. In this case, you have constructive interference. So in this case over here, the answer is half a wavelength because that worked. So it equals to half a lambda. Lambda being 375, divide that by 2, is equal to 187.5 nanometers. Okay.
Just draw that diagram. That's good.
Mm-hmm. So it's always going to be half a wavelength or a quarter wavelength. Now, as your teacher changes the angle of the light source, the light you observe changes color. Why? Well, right now, you guys have to understand, that's the wavelength of green light, 375. If I change the angle, guys, look. If instead of using this angle over here that's straight on, now this is the angle. Is that the same distance as before? No, it's not the same distance. In fact, it's a longer distance. So basically, rather than being green, you might see yellow, orange, or red. Because the distance increased, that means the wavelength. So distance increased, wavelength increased. So now that's going to equal to yellow, orange, or red, which basically means that you have different colors coming out at different locations. And an example of this would be like an oil slick. Do you guys understand what I mean by an oil slick? You know, when sometimes you have oil on top of water, you see the rainbow on top? And the reason you see the rainbow is because when you're looking at the oil slick, technically you're looking at each part at a different angle. So because you're seeing each part at a different angle of the oil slick, it reflects back at a different color for it, which is why you end up seeing a rainbow.
How do you know if the wavelength increases or decreases?
Well, from this distance to this distance, doesn't this require a longer wavelength? Okay, that's fine. Okay? What other questions do you guys want me to answer for the practice exam before I move past it? Is there anything else? Any other multiple choice questions? Any other part 2 questions? Otherwise, you guys should be going through these on your own. Nothing? Brian? Number 7? Oh, I'm sorry that Brian did it ahead of time. Maria? Okay. 7's it's actually a pretty straightforward question. So it's actually pretty easy. I'll go through it fast. Bohr model. What did I tell you is wait, did we do this in class?
No. Yeah, we did. Yeah, not in our class.
Maybe not in your class? Okay. No, I definitely did it in the morning class.
No, you didn't. Not in our class.
I I could have sworn I did this question already.
You did it. You did it.
I did in 6th period? I'm almost positive I did in the morning class also, but maybe I didn't. Anyway,
I was awake.
doubtful. Anyway, whenever you see a Bohr model question, what's the first thing you should always do? Convert to energy. Even Theo says that we did this one.
I said me.
Oh wait, no, that was probably I was actually on Thursday.
Anyway,
Friday.
so I'll go over this very, 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 very quickly. You have two wavelengths. E equals hc over lambda, 1240 over 400 is equal to 3.1 electron volts. And then we have 1240 divided by 700, which equals to 1.77 electron volts. Okay, so that means that during jump 1, it gives off 3.1 eV. During jump 2, it gives off 1.77 eV. So how much energy does jump 3 give off then? In this case, if you just look at it, just add them all up basically, you know that it has to give off, it's terrible that I use red because it should be a higher frequency, but whatever, 4.87 electron volts. So what's the wavelength of that? Well, we set that back equal to hc over lambda. So lambda, 1240 divided by 4.87. 254.6 nanometers. Okay, so that's the answer part A. 254.6 nanometers. Okay. Now the photon emitted during transition 3 is then incident on a surface with a work function of 2.1 electron volts. So we know the energy that's being given off of the photon was again 4.87. The work function is 2.1. They ask us what's the kinetic energy of the electron. Kinetic energy of the electron is equal to energy of the photon minus the work function. So that simply is equal to 6.77. And if you want to solve for the de Broglie wavelength of the electron, well, if you know the kinetic energy, well, the de Broglie wavelength, first of all, you have to set the two momentum formulas equal to each other. H over lambda equals to mv. So lambda is equal to h over mv. But we don't know v. But we know kinetic energy. So we can set this equal to 1/2 mv squared. But the only thing you have to be careful about is that kinetic energy has to be in joules. So if using the conversion factor, 1 eV is 1.6 times 10 to the negative 19 joules, you get the energy is 1.0832 or 1.08 times 10 to the negative 18 joules equals to 1/2 mv squared. Okay, you solve for the speed and then you solve for the wavelength. That's me flying through this question. You okay with that, Brian? Okay. What did you say? Incident means it shines onto or it hits. Okay. Nick. Did I add them instead of subtracting them? So I meant 2.67. Sorry. 2.67. So therefore, 2.67 times 1.6 e negative 19. 4.27. Sorry about that. Okay. All right. I'll help you guys with thermodynamics no card then. Sure. Okay. So for thermodynamics, You need one?
I'm saying, I'm asking if anyone needs
How many of you have made a thermodynamics note card already?
I don't remember.
So those of you that made it already, just help me out in case I forget something.
Before you said something about
It's always the same during refraction. Okay. There's a lot of formulas for thermodynamics. It's a large unit, unfortunately. So I'm just going to define each formula, and then we'll do one quick small example of each one. I think that might just be easier. I'll write down a couple of notes for each one as well. Delta L equals to alpha L naught delta T. This is thermal expansion. This never appears really on a part 2 question. It's really only a multiple choice question. Okay. Now it depends on what you really need to solve for, but really the most important note is what I mentioned before, is that delta L is directly proportional to delta T.
What is delta L?
Change in length. Meaning that if you have double the delta T, you have double the delta L. Triple the delta T, triple the delta L. So I'm not going to go too much more into it, but just understand that those two are directly proportional to each other.
So where would you see that in like?
We did a question like that in the multiple choice before, I think, didn't we?
We did, yeah.
Okay. So, and that's the most common type of question. So I could even give you guys another question where you don't have to copy this down, just watch. A metal bar expands 0.3 centimeters when heated from 100 degrees Celsius to 150 degrees Celsius. Right? And they can ask you a question like, and this was, I believe, a real AP question. How much would it expand if heated from 425 degrees Celsius to 475 degrees Celsius? Like I said, you don't have to copy this down because once you hear the question, hopefully it'll make sense. But a metal bar expands 0.3 centimeters when it's heated from 100 degrees Celsius to 150 degrees Celsius. How much would it expand if heated from 425 degrees Celsius to 475 degrees Celsius? Demi?
0.3
Still 0.3 centimeters. Same delta T, same delta L.
You don't need to convert to Kelvin.
In this case, part of the reason I don't convert to Kelvin is because it's always going to be delta T. So 100 Celsius to 150 Celsius is technically 373 Kelvin to 423 Kelvin, meaning that the delta T is still the same amount. So technically, everything should always be in Kelvin. But the only reason they don't care for this formula is just because it doesn't matter. Okay. H equals Ka delta T over L. This is a formula on your reference table, again, that usually appears on the part 1s, not on the part 2s. This is about rate of heat transfer. So when I say rate of heat transfer, it's really saying, in a sense, Q over T, or even power, we could say. We don't really talk about the power. So H is the rate of heat transfer. It depends ultimately on the cross-sectional area versus the length. There's usually not really a hard question on this. You just, if you know the formula, you should know that it's directly related to area, inversely related to length. Now, when I talk about area and length, I mean, you could talk about, and it always flows from high heat to low heat. You can write that down, actually. Q always flows from high T to low T. So you don't have to draw this, but if you want to draw, you can. You have a high temperature and a low temperature. Okay. If you connect it, basically the cross-section area is the area. This is the length between the two places. And K is the thermal conductivity constant, which you don't really need to know because it's based on whatever the material is. But the real life example that I had given you guys was really about the windows of a house. So we have a house, and there's a window. Okay, the thickness of the window is L. The area of the window was A. And you have high temperature inside, low temperature outside, or vice versa. So you end up having some sort of heat transfer going through. Okay, so there's not much to know about the formula, but if you memorize the formula, there's always one question on it in every AP. In fact, I didn't see it in this one. Was there a heat transfer question in this one? I'm sure there was. Let's see. Heat transfer.
Actually, I don't think there was.
There might not have been. No, they didn't. But you can see that's how rare it is, okay? If you do the 2004-2009 AP questions, you'll see it in there. There's at least one question on each of those.
For expansion, when it's hot, it expands, and when it's cold, it contracts.
That's simple. The only thing that breaks that rule is when water freezes.
It expands.
It expands. So but technically, water actually does contract a little bit when it starts to freeze, but then at a certain temperature, it actually just bursts out when it forms its rigid structure. Okay. Kinetic energy equals to 3/2 kBT. I'll do this. V RMS is equal to 3 kB over m square root, or 3 RT over U, I think is what they use. Something like that in your reference table. This is ultimately about the ideal gas laws. Okay? You have to know what the ideal gas laws are, but it's not really too terrible.
Is that K sub C?
Yes. The ideal gas laws basically state that all molecules are far apart from each other. Are far apart.
Is that RMS?
Yes. The gas molecules are far apart. They only do elastic collisions. And they move in a straight line. All right, no outside forces. What'd you say?
Negligible volume.
Negligible volume, which is really gas molecules are far apart from each other. Same idea. Okay, the gas molecules are so tiny that every gas molecule is really far apart from each other. Yes.
On the reference table, it says that VRS is equal to 3RT over M.
Capital M?
Yeah. So and then
The other one's mu?
yeah, 3K K voltage constant times T over.
Oh, I forgot the T, sorry. Over mu, was it?
Yeah.
Okay. Now we'll talk about what it means in a moment. Yes?
Since it's elastic collisions, does that mean that the kinetic energy is the same for all of them, or just the average?
No. It means that the kinetic energy is conserved. So it can pass the kinetic energy from one. So a fast one hits a slow one, the other one might be moving faster, it gains the kinetic energy. The kinetic energy is conserved. It doesn't dissipate into heat or something else. Okay? And the last thing is that, yes?
What does it say in the last one?
No outside forces, elastic collisions, gas molecules are far apart. And that kinetic energy ultimately is directly related to temperature. Okay, which is what 3Ke equals 3/2 kBT is. Now, understand that 3Ke equals 3/2 kBT is talking about one molecule. One gas molecule. But because we are talking about one gas molecule, about the average kinetic energy, AVG, the average kinetic energy of one gas molecule, then we can always do Ke equals to 3/2 kBt is equal to 1/2 mv squared. But that ultimately, that crosses out, is how we derive that formula over there. We get speed is equal to 3 kBt over m square root. But rather than using m, which is the mass of the gas molecule, for some reason on the reference table they represent it with a mu. But the mu just still means mass of a gas molecule. So there's not too much to know about this, except for, I mean, if you double the temperature, by what factor does kinetic energy change? Twice, right? Everyone sees that? Mm-hmm. But if you double the temperature, by what factor does the speed change? Radical 2. But it's not doubled. Did everyone understand that? Did anyone not understand what I just said? If I double the temperature, I double kinetic energy. If I double temperature here, because it's underneath the radical sign, I'm pulling out a radical 2.
Wait, but then wouldn't that be 3/2 or no?
No, because remember we make everything, whenever we do a multiply, make everything go to 1, okay, including the whatever is part of the formula. Okay. Now, the one important formula that's not on your reference table, but you need to know. Now, this talks about one gas molecule. But if you're talking about the entire gas inside the system, rather than doing kinetic energy equals 3/2 kBt, we have a derived formula of U is equal to 3/2 nRT. And on our, and rather what's more important,
That's the kinetic energy of the whole system?
that's the total energy, right? That's the energy of the total system. And whenever we're solving for a change in energy, it's really still based on the change in temperature. Okay, so delta U equals, or U equals 3/2 nRT. So overall, that second formula we have for 3RT over M is based off of this total energy. So you have 3 times R times T, but in this case, this is the molar mass, the mass of 1 mole, rather than a single mass of a single molecule. But they both solve for the average speed of the molecules themselves. And honestly, I've never seen them use 3RT over M anyway. So 3 kBt over mu is much more important. Okay. Any questions about this? If we are to talk about the ideal gas laws, we also have to talk about, of course, the most important formula, which is Herbner. So, with PV equals nRT, with Herbner, okay? Understand, of course, your proper units. For us, we use Kelvin, meters cubed, and pascals, or newtons per meter squared. R will always be given to you as 8.31 joules per mole Kelvin. In chemistry, you might have seen R. Oh yeah, you guys didn't use Herbner in chemistry. Never mind.
Yeah, sure.
However, in chemistry, what you guys did see was its derivation. If you divide both sides by T, you end up with PV over T equals to PV over T. Because since they both equal to NR, it's a constant. And because it is a constant, the most important fact you should write down about this is that all multipliers must cancel out. I'm going to do one easy PVT over question, and then I'll do 2 harder ones. Example. Again, you can choose to write down or you can choose not to write down. It doesn't really matter to me. In a rigid container, the temperature of the gas is decreased to 1/3 its original value. They can ask a couple questions like, what happens to its pressure? What happens to its volume? What happens to its density? In a rigid container, the temperature of the gas is reduced to 1/3 its original value. What happens to the pressure, volume, and density?
What's the
So-
point of mentioning that it's a rigid?
Well, can someone answer that question? What does it mean by the fact that it's a rigid container? Lene?
Doesn't that affect how the molecules
No. Well, technically, yes, a little bit. But there's something more, even more basic than that. If it's a rigid container, Fatima,
the volume doesn't change?
the volume does not change. Okay? So in this case, volume, no change. Now, by the way, I'm just going to skip ahead to something else. But if there's no change in volume, that means that work is automatically equal to 0 too, right? Because work is equal to P delta V. And this is called an isochoric reaction.
Oh my god.
Not that you may or may not want to memorize that. Okay, anyway. There's no change in volume because the fact is it is a rigid container. So, what does change? We said we have 1/3 the temperature. Volume has no change whatsoever. Therefore, the pressure must have. Does 3 divide by 1/3?
Wouldn't it just be 1/3? Yeah.
It'd be 1/3. Because 1/3 cancels out 1/3. So when you have 1/3 the temperature, you end up with 1/3 the pressure. What happens to density? What happens to density? Right?
Is it not change?
Why?
Because if the mass is the same and the volume is the same, there's no change.
Same mass over volume.
But isn't negligible?
Doesn't mean that there's how we still calculate density by doing mass divided by volume.
Yeah.
So the mass stays the same, so the volume has to still stay the same.
Right.
You're right. The mass is relatively negligible, but gas molecules always fill up their space. Okay, how is that as an easy question? Not that easy.
Nope.
Here's a harder question. The volume of a container is halved while the pressure is also halved. The volume of the container is halved while the pressure is also halved. What happens to temperature, density, and the speed of the molecules? The volume of the container is half, while the pressure is also half. This is actually similar to an athletics question. So PV over T. What happens to temperature? Maria?
Is it 4?
What do you say?
4?
Is it 4 times greater?
Oh, I thought it was.
Well, the pressure is volume is halved. Pressure is halved. This does not stay the same, and it's not 4 times greater.
It's 1/4.
It's 1/4.
That's what I thought, but then you said it was like
1/2 times 1/2 is 1/4 on top. Therefore, you need to be 1/4 on bottom. So you have 1/4 the temperature. What happened to density? What happened to density of the molecules? Maria, would you like to try again?
No.
Siddhan?
It doubles
Why is it double?
because it's more volume halves like
So you have 1/2 the volume, good, which means that you have 2 times the density. Good. How about speed? Now this is the important question here, because this is the actual AP question here. What happens to Vanessa? Almost. Not radical 2. Almost. What formula were we using?
K equals 1/2 mv squared.
Well, you can use KE equals to 1/2 mv squared, but this is an easier formula to use besides that one. But in this case, so what happened? How did you get? What did you do here with this formula? It's fun to use this formula.
I did multiply, so I did like 1 is 1/2. Oh, I did 1/2 because constant.
You make that one also. So therefore, what do you say?
Why did I just do 1?
Well, how much did the kinetic energy change by?
I thought it was 1, but kinetic energy was considered.
No. This is, first of all, the temperature changed. If the temperature changed, because you have the formula. So based on this formula, right, the temperature changed. So therefore, Siddhan?
maybe 1/4 the speed.
No, it would not be 1/4 the speed. It would be 1/4 the temperature, so it's 1/4 the kinetic energy. But it's not 1/4 the speed.
Would it be the square root of 1/4?
What's the square root of 1/4?
Oh, it's 1.
What's the square root of 4?
2.
Oh.
So 1/2?
So 1/4 is really equal to 1 times 1 times 1/2 squared. So overall, I purposely picked this hard number because you guys are terrible at square rooting fractions. But really, square rooting fractions, same thing as square rooting a regular number. Square root of 4 is 2. Square root of 1/4 is 1/2, which is 1/2. Anyway, in this case, the speed is half of its original amount. 1/4 kinetic energy, half the speed. Okay, hopefully that was hard.
Thanks.
One last thing about this formula, or actually more than one last thing. Understand that technically, even with PV equals to N R delta T, you can always have a question. Normally the number of moles doesn't change, but what if a container sprung a leak? For example, we have some sort of container that held the gas molecules inside, and a hole developed. That's a giant hole. And half the gas molecules leaked out. Okay? It's a rigid container. After half the gas molecules leaked out, they plugged up the hole. Put in a little plug. Okay? If half the gas molecules leaked out, ultimately, what variable changed? So in this case, well, it's a rigid container. So did the volume of the container change overall? It's not the volume that changed. It's the pressure. If you think about that, it makes sense. Pressure is the molecules bouncing against the walls, right? And if you have half the number of molecules bouncing, you would really have half the pressure. So in this case, delta N directly related to the change in pressure. So you have lots of different situations that you might, I mean, the problem is there's an infinite number of possibilities. But just in its most basic form, understand Pervner and PV over T. Not even there yet. I'm almost there. One last thing for PV over T. It can always be applied to these graphs. Isochoric, isothermal, isobaric. Okay. No change in delta V is equal to 0. Delta T is equal to 0. Delta P is equal to 0. Bye, Demi. Of course, if you talk about in terms of the laws, certain things are important. For example, when delta V is equal to 0, I know that work is also equal to 0. And when delta T is equal to 0, I know that delta U is also equal to 0. So right, if I want to talk about in terms of the laws. But if I want to talk about in terms of PV over T, don't forget you can always use Pervner for PV graph if you know the number of moles. Otherwise, you could always do PV over T equals PV over T. So this was location 1, 2, and 3. I could do P1 V1 over T1 equals P2 V2 over T2. Because between 1 and 2 is the same volume, I can cross that out. Okay? Or if I have P2 V2 over T2 equals to P3 V3 over T3, I know that B is an isothermal line. So that means temperature crosses out. Anyway. And it's not uncommon, of course, to have a part 2 question that looks like this. Yes, Fatima?
If you're trying to find the work, would it be inside of the triangle or underneath the triangle?
Area underneath.
No, trying to find the work of this entire cycle, it would be the area inside. Okay?
So if you were
Right.
doing like 1 to 3.
What do you say? In this case, you wouldn't be able to find the area very, very easily because it's not an easy shape.
But if it, wouldn't you do it underneath the graph?
If you're looking for just 3 to 1 to 2,
Okay.
right? If I was looking for 3 to 1, it'd just be the area underneath over here. If I'm doing 3, 1, 2, 3, that's the entire area.
And
Okay.
adiabatic.
I'll get there. If you guys want to write down adiabatic, that's fine. Adiabatic means that there's no heat transfer. Q is equal to 0. You're asking me when you should write this on your note card already yourself. Vanessa?
You know how you said the top right is the highest temperature? If there's no top right, like in that one, would it be 2 or 3?
Well, it could be either one, and you simply base it on, well, remember, Pervner, PV equals nRT, right? Really, PV is based on, is equal to T, right? So if I just made up a couple of numbers here, for example, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. Okay. So in this case, location 2 would be 3 times 1, while location C over here is really 1 times 4. So you can see that location 3 has a higher temperature than location. Actually, that can't even be true in this case, but because it's isothermal. But if it wasn't isothermal, that's how you do it.
Okay, yeah.
Okay. And just erase all that because this is isothermal. I just ruined my own isothermal line. But hopefully that answered your question. Okay. Anyway, I'm just having fun throwing these around. All right. All right. PV graphs. And delta U equals Q plus W. The most important thing for delta U equals Q plus W is understanding when is positive, when is negative. Okay? But otherwise, I mean, the formula itself is easy to use. But it's hard to understand when things are positive, when things are negative. So let's do a Carnot cycle.
Oh,
Isothermal, adiabatic, isothermal, adiabatic. Okay. 1, 2, 3, 4. 1, 2, 3, 4. You have to be able to make a delta U equals Q plus W chart because that comes up a lot. When is one thing positive, when is one thing negative, or when is it 0? We'll do this a couple times for a couple different graphs, but right now for reaction 1, it's an isothermal expansion. What should I automatically know? Okay, it's isothermal expansion. Giordani? Change in temperatures equals 0, so what does that mean? So delta U is equal to 0. It's an isothermal expansion, so what else should I automatically know? If it's isothermal expansion, volume is increasing. Giordani?
Is heat being added?
Well, yes, he is being added, you're right, but before I get to that idea, I should also understand more obviously that, Hamza?
work is being done by the system.
Work is being done by the system, so it makes it negative. So 0 equals what plus a negative number? Has to be positive. So heat was being added to the system, you're right. Okay. An adiabatic expansion, what do I know? It was an adiabatic expansion. Maria?
There's no heat transfer.
There's no what?
Heat transfer.
There's no heat transfer, because that's what adiabatic means. But because, again, it's an expansion, therefore, work done by the system, so therefore, delta U must be negative. Because negative equals 0 plus a negative number. Isothermal compression. What should I know automatically? Isothermal compression. Well, because isothermal, I know that delta T is equal to 0. And because it's a compression, work is done on the system. That's positive work. So, therefore, this must be a negative number, because negative plus a positive is 0. And adiabatic compression, in this case, Q, of course, is equal to 0 again. That's for the positive work. So this equals to a positive number. Okay? When would work equal to 0? When would work equal to 0? Vera? When there's area underneath. Whenever it's a vertical line, work is automatically equal to 0. Okay. So beyond that, I'm not really going to do too much more with the laws of thermodynamics because you have to understand how to be able to read it. There's a positive negative work, and just plug into delta U equals Q plus W. Kim, you look like you're anxious to leave. Would you just like to leave? Okay, I'm glad you have somewhere better to be right now. Maria?
What is the zero flaw? Do you need to know that?
No, you don't need to know zero flaw.
Or what is it?
You don't want to cross your this one.
Zeroth law, I believe, was energy can neither be created nor destroyed. Wasn't that what it was? Or is it? I'm pretty sure it's just conservation of energy.
Yeah.
Okay? But I might be wrong. I apologize if I'm wrong.
It's correct.
Last part, which is the part that a lot of you guys struggled with, is second law of thermodynamics, or really about entropy and efficiency.
Oh, that's not important.
Yes. Now the formulas for efficiency are E is equal to work over QH, and EC is equal to TH minus TL over TH. High minus low over hot, or hot minus cold over hot. Same thing. Okay. Now, yes, Vanessa.
In a question, if they ask about efficiency, can you use either one?
No. If they say maximum possible efficiency, or they say ideal engine, or Carnot engine, it's obvious. Okay, but if those are the key words here, then you can use Carnot. Okay, otherwise every other case is E equals work over QH. But this formula is easier if you really understand what QH really means. QH is the total energy put in. And what does the energy ultimately turn into? It turns into work and QL, meaning that it's the energy that's wasted. Okay? So that's why you really have QH equals to work plus QL, or work is equal to QH minus QL. But the fact is, it's the total energy put into the system. Some of it gets used for work, the rest of it's wasted. And a lot of times, this formula can get changed to be work over time over QH over time. The rate at which heat work is being done, the rate at which energy is being added into the system. So this is being in terms of power and watts instead of joules. Okay. The easiest way to talk about this really is to do, I guess, a practice question. Would you guys like to go over a practice question together now? And that way we can put it onto a note card. I don't know if you guys even have room on your note card anymore at this rate. Actually, yes.
Can I have our rooms?
What'd you say?
Our rooms, room numbers.
Did I email it to you guys?
Yeah, but it was a long time.
Oh, I'm sorry. It was a long time ago. I emailed you guys all your rooms. In fact, I emailed you guys your English room, your American room, and your physics room, didn't I?
Yeah, you did.
Yeah, I did. Look through your email. If I find it again, I'll forward it to you guys.
What was the subject of it? AP room.
Probably like AP rooms or something like that. Okay? Alright. Otherwise, off the top of my head, I don't know what your room numbers are because I figured I gave it to you already.
AP physics room schedule, I got it.
Would you like to say out loud what a physics room schedule is then?
Monday, May 12th, Physics B. 2:11, Vedette to Dianarine. 2:15, Ijaz to Lee. 1:27, McCarty to Rodriguez. Library, Sadra to Zimmerman.
What's the party to Rodriguez?
Alright, Vedette to Dianarine, 2:11. Ijaz to Lee is 2:15. 2:15. McCarty to Rodriguez, 1:27. Sadra to Zimmerman. Library.
2:15. She's at the student store too.
I love the library.
Alright. So, overall, here we have, bye guys, 2.2 kilograms of water, initially at a volume of 2 meters cubed, and a pressure of 3 times 10 to the 5th. And that's actually given to us on the graph over here. So I'm reading it to you guys, but technically I'll tell you guys. The molar mass of water is 18 grams, and the water vapor can be treated as an ideal gas. And this is one thing actually I didn't cover before that you guys should write down into your note card as well. Let's put this on here first. They mentioned that the mass is 2.2 kilograms, but that the molar mass is equal to 18 grams. Now, why is that important? You guys remember this from chemistry?
No.
The number of moles.
It's 1.6.
All right, number of moles is equal to the mass divided by.
That's what N is.
Yes, N means number of moles. Mass divided by molar mass. But of course, are they the same unit right now? No. So this would be 2,200 grams divided by 18 grams.
Why wouldn't it be kilograms?
You can do kilograms, I don't care. Either way, you get the same answer of 122.22 moles. Okay, that's the most important piece of information, and that's a formula that's not on your reference table, but they assume that you know it. Whenever you're looking for moles, just take the mass divided by molar mass. So molar mass is mass of 1 mole. That's the total mass, so that's grams per mole, really. Okay. So now that we know N, they want you to find what's the temperature at point A. Get to work. Okay. What's the temperature at A? Remember, when you have a PV diagram, you can always just read off of it. Now, in the end, if you don't want to solve the whole question, you don't have to. I don't care if you do or not. At the very least, you should be able to write down what's the right formula to solve for temperature. Because you should be able to look at any PV graph, especially with the number of moles, and solve for temperature. So how do I find temperature at A? Can someone tell me right now? Danish?
You could do it from Brebner. 3 times 10 to the 5th times 2 is equal to 122.22 times RT, or the constant.
And you can use Pervner to find the temperature at A or the temperature at C, ultimately. Okay? So I just want you guys to understand, if you know the temperature at A, 0.5. Okay. Let me just close this one. Okay. Anyway, so overall, you use permanent to find temperature at A, you'll use permanent to find temperature at C, and then they ask you, what happened to the internal energy from point A to point C? Increase, decrease, or remain the same? You guys will all say it. Increase, good, because temperature increase. Right, delta U equals 3 times N or delta T. Okay, or energy is directly related to temperature if you can't remember the formula. Anyway, that's 3/4 of the question. Last question, here's the easy one. How much work is done from A to C? How do I calculate work? And this is, again, something that you guys can just draw onto a diagram right now just to remind yourselves, because you don't really need to solve it for real. Fatima?
Area under AC, so that rectangle.
Equals to positive work or negative work?
Negative.
So I'm just trying to show you guys that, okay, A to B, technically no work was done. All the work was done during B to C. But I just want you guys to understand, just write down a few notes, per to find temperature at A or the temperature at C. If you wanted to, you could use delta U equals to 3/2 NR delta T to solve for the delta U overall. And if you knew the work from over here, what could you solve for next if they had asked for it? If you had solved for delta U, you had solved for work, you could then solve for Q. Okay? So these are just different ways of solving these. So work is equal to area. So then Q would equal to delta U minus the work. It will really be minus the negative work. Anyway, so this is just steps. Step 1, find change in internal energy. For step 2, find the work from the area. Step 3, Q. Let's do one more. Oh, actually, this is a good one. In fact, I highly recommend, we're not going to solve this whole question, but I highly recommend right now you guys just at least copy this diagram.
I just want like this. I just pop back into Oh, that's intense. See, how did you get so good at drawing? Not that you drew this, but like whatever you draw.
I obviously practice at home all the time for my daughters and my son. I just draw little physics diagrams for them with 3x diagrams and motion
They're
maps.
so lucky. They're gonna have a really good tutor.
Just so you know, that usually people don't like to be tutored by their own parents.
Really?
I remember one of my students in AP Physics was the daughter of North's AP Physics teacher.
Yeah.
And he's a brilliant physics teacher where he even won awards for physics teaching. But
you won an award for physics teaching.
Now, maybe. But I'm just saying, but he won an award, but she refused to ever get help from her father, no matter how brilliant he was and how great he was at teaching it.
That's so
And in the end, I mean, she liked me as a teacher. She said, "I'll just go to you for extra help," but she never came because she was lazy. And in the end, she got a 4 in the AP, so her father wanted to punch her. Because she really was smart enough to get a 5. She's just lazy.
Oh well.
Okay, now the reason this diagram is important is because it highlights a couple things here. Overall, we can see that right now in state 1, it's just air pressure. This is basically air pressure right here. So what that means is that outside the cylinder, you have air pushing down on it with air pressure.
That was an open cylinder?
It's not open. There's a lid over here, a freely movable piston that moves up and down based on the pressure of the gas inside. Okay, so right now,
On the top, it's exposed to air.
yeah, the top is exposed to air, yes. And the inside, so that means the gas particles themselves are pushing back out with air pressure. That's simple enough. This is balance, which is why this is also hanging right there. But when they put a block on it, it squishes it down. You guys can see that, right? And that makes sense. If you think about this gas inside, it's like a syringe. You can only, if you close one end of the syringe, you can only push the piston inside a certain amount because you're compressing the air. So they ask, really, what's the total pressure in state 2? Well, what's pushing down on it? We have air pressure still pushing down, and we have the block pushing down. But is block, we know the weight of the block, but is force the same thing as pressure?
No.
No. But how do I relate force to pressure? P is equal to F over A. So the total pressure that's pushing down at that point is really equal to F over A, the force of the block. In this case, it's pushing down in this area over here, plus air pressure. So the area of the block of the cylinder was 1.2 times 10 to negative 2. Okay. So in this case, I just want you guys to understand, because this has appeared on 3 different problems, where you have to find the total pressure. You have to add up the pressure, the force over area of the block, plus air pressure, and you find P2. In this case, P2 is equal to 25 divided by 1.2 times 10 to the negative 2 plus the air pressure 1.02 times 10 to the 5th 1.041 times 10 to the 5th pascals. How is that? You guys okay with that? Now, the next question was, what's the volume? How would I solve for the volume in this case, for V2? Come on, this is the easy question. I helped you guys solve for the pressure at state 2. How do I solve for volume now? What formula relates it? Lene? No, you guys said something equal to each other. What are you saying equal to each other? You just said P1, V1, or T1 equals to. But how is this possible? You can't divide by 0. It's not in Kelvin. Have to be careful. In this case, the temperatures cross out anyway. But remember, temperatures have to be in Kelvin. So you should write a note to yourself just in case. In this case, temperatures cross out. You know the new pressure. You guys can easily solve for the new volume. Of course, we're not going to solve for it, but I just want you guys to note that, okay? Now, the thing is, did the temperature change? What kind of reaction is that? Isothermal. Okay, and that was actually part C. They actually asked you what kind of reaction is that. Anyway, let's move on. Let's move on. We're done with thermodynamics for now. Unless you guys want me to do an efficiency question. Yes, Maria.
Okay, so if it's isothermal, is it automatically adiabatic?
No.
So what is
Adiabatic is Q equals 0. Not temperature for energy.
Okay.
Okay. What else do you guys want to go over? Or do you guys want to do some practice questions on your own and then ask me?
I like that.
Practice on your own? Okay. You guys can work quietly for half an hour. Let me check Schoology right now. Hold on. Just to make sure that that works. I know you guys are probably brain dead right now.
Take a 5-minute break.
No, I got momentum, Brian.
I just like snap back and forth.
Available now. I can do electricity, that's fine. Or I can do momentum. Take care, Joe. Bye, Alexis. Yes.
Electrostatics.
Thank you. I owe you $3.
Yeah.
So who has
So why don't we just
Okay, I'm gonna take the 2 in here and get a water
what's
bottle.
your house address?
What do you say?
Taking the 2 in here and getting a water bottle.
Okay.
12?
All right. Electricity?
Yeah.
Electrostatics.
Did you guys do electrostatics on your own yet, or no?
It's hard.
No, momentum part.
No,
No,
it's
Electrostatics is so much harder.
I'm not ready to get it on.
You can work on your own, or you can pay attention for electricity if you'd like. I don't care.
How far is it?
Yeah.
It's not.
It's like a 5-10-minute walk.
Okay. By the way, please take more bagels. If you always want these bagels home for your parents, take them for your parents, your brothers, your sisters. Otherwise, it's just gonna get thrown out. What'd you say? I'm a legend in what?
In these streets, you're like driving the fast.
Everyone said no. Well, you teach it to me? Yeah, I told you that. Yes, I told you. So you do like a good job? Yes.
All right.
You have Brian taught me. Okay. Don't understand. You will. You taught me that time for like 2 seconds. And then I got it.
Okay.
I felt like
It's Johnny's birthday today.
See, I missed the multiple choice, but I actually did it.
It's recorded.
Adela,
Up to
Adela,
65.
every question.
Almost every question.
Like, I got a lot wrong, and I was really upset. I did it for like 40, I did for like 50, and I just got sick of it because I had so many wrong. It was really sad.
Borrowing.
Adela, can you what you want to
Thank
paper one day?
You're welcome.
No, you want to ride? Today or tomorrow? I don't really know. I'll do today.
All right.
Yes.
I'll wait another couple of minutes for you guys to sit down, and then I'll start electricity. I guess I could give the bagels to the cultural study kids downstairs.
No,
They'd be so happy.
Who's dancing today?
Logo and Lionel is there.
I think we finished.
All of these are garbage. Everyone's so thirsty.
Wow, there's a lot less food than
The thirst is real. Real talk. Real talk.
Unless they left it in the car.
Oh, I was about to tell you 3 times a day.
Unless they left it in the car.
Wait, Mr. C, do you want me? I'm going downstairs. Do you want me to take them? Mr. C, I'm going downstairs. Do you want me to take them?
No, let's leave it now. I'll read later.
Over there.
All right, here we go. Let's go. Electricity.
Why are you closer to me? Why?
So, basic formula-wise, there really isn't too much to do. There really aren't that many formulas.
They're like similar. They're so similar. I get so confused.
That's electricity. I'm doing electricity right now.
Electricity, was that neutral?
I equals to Q over T.
Oh, wait, that was one with the capacitance and all that?
V equals IR.
Yeah, I made, but what is it?
R equals rho L over A.
Yeah, I made a card for that.
P equals to VI. All right, let's go over basic formulas first. Okay? Any sort of little notes you guys should know. So, basics-wise, you guys have to understand for I equals Q over T, charge is not the same thing as number of electrons, right? One electron is equal to, or one proton, 1.6 times 10 to the negative 19 coulombs, which is something that's always going to be given to on your reference table. For V equals to IR, understand that V and R have no relationship with each other, meaning that V is directly related to current, resistance is inversely related to current, but neither of them affect each other. The stronger the potential difference, the greater the current. The greater the resistance, less current you have. Okay? Now, this follows a basic graph, V versus I, and the slope is equal to resistance. Now, just in case this comes up, but I doubt it will, any resistor that follows that direct relationship is called an ohmic resistor. Ohms, of course, is a unit. Ohms is a unit for resistance. Some non-ohmic resistors might simply, well, start curving one way or the other.
Do they have those on the AP?
Rare, I don't think so. Okay, but in general, just understand slope is equal to resistance. For R equals to rho L over A, this formula is straightforward enough. that resistance is directly related to length and inversely related to area. However, what's not stated is that the resistance is also directly related to temperature. Because in general, when the temperature goes up, the resistivity also goes up. And resistivity itself is like density, in that it's a constant for that substance. But it can change based on the temperature of the medium itself. So it's directly related to length, directly related to temperature, inversely related to area. So one possible question was actually one of your test questions. In fact, maybe I'll just bring it up right now, because a lot of people got this one wrong. Let's see if I can find it real quick. My drive, the assessments, Unit 16 test. Oh, never mind. It was in the practice test I gave.
The fake test.
The fake test. I don't know where to put the fake test. That's okay. I'll do it this way. I apologize. I'm just too lazy to actually write this onto the board, so I'm just going to copy it directly on. It's right over. This is what you get for making a fake test and not a real test.
It's like the row of resistivity constant directly proportional to T2.
There's one good question.
Is that constant directly proportional to T2?
Yes.
So the like key thing
I didn't show the graph. I was going to that get matchable. Yeah. If not, you could ask like.
No, track is after practice.
Track practice is over. It's finished a while ago.
Yeah.
Track is over?
It's a playoff game, yeah. No, I mean I tracked it. Like it finished
Wait, where's the
at
game at?
10.
It's at parallel. Actually,
Okay.
Forget it. I give up. All right. I'll just write this question. How to increase current in a circuit? What are some ways? Okay? I want you guys to understand this is going to be based on all the formulas that I've talked about so far. What's one way?
Decrease resistivity of the wire.
I could decrease the resistivity of the wire because that would be decrease in resistance. Good. Danish?
Increase the voltage.
I could increase the potential difference that's connected to. Good. What else can I do? Fatima?
Increase the temperature.
Increasing temperature would increase the resistance.
Oh, so then decrease.
So really, I would like to decrease the temperature. Okay, sit down.
Would putting it into series increase?
Wouldn't that decrease? Because we have put resistors in series.
So putting them parallel.
So I could put it in parallel. Put resistors in parallel, because that would decrease the overall equivalent resistance. What else can I do, Danish?
Increase the length of the wire.
Increasing the length of the wire would increase the resistance.
Oh.
So really, I would want to decrease the length of wire. What else? What else can I do? Danish?
Increase the area.
I could increase the radius or diameter or basically the area of the wire. So 6, 5, and 1 are all about decreasing resistance. You decrease resistance based on the formula of rho L over A. Or you could increase the potential difference, or you could decrease the temperature, or you could put the resistors in parallel. Okay? So I just want you guys to understand the relationship between all these things and how they affect current. Fatima?
Could you decrease the time or increase the charge?
Well, technically, yes, I can decrease the time based on I equals Q over T, but that's not really about changing the circuit, though. Okay? All right. So hopefully that made sense. Let's take a look at P equals VI. Well, P equals VI is very commonly used in conjunction with V equals IR, because you might have to solve for the voltage or current of one based on the resistance. However, the hard part of P equals VI is knowing the graph. Power versus resistance is easy. As resistance goes up, power decreases, right? The more resistance there is, the less current there is, less bright the light bulb will be. Ultimately, as I had said to someone else, that's how a dimmer switch works, right? You guys have a dimmer in your household. Whenever you use a dimmer, all you're doing is increasing the resistance in the circuit, which decreases the light.
Are you serious? That's how it works.
That's all. This is a variable resistor. And then when you decrease the resistance, you increase the current, makes the light bulb brighter. Anyway, but power versus voltage or current. What should the graph look like? And they are related. As one goes up, the other goes up. But it's not direct. It's exponential. Because normally, if you double the voltage, what happens to current? It doubles also. Meaning, if you double one, you automatically double the other, so it becomes exponential. Okay, so I just want you guys to understand, power is exponentially related to voltage or current. Okay? Also, of course, power, which equals to V times I, can ultimately be set equal to work over time. So whenever we talk about electrical energy as W, it's relatively equal to power times time. And because we are talking about work and energy or power, we can always relate this stuff back towards efficiency. Efficiency in thermodynamics, as I said, was equal to work divided by QH. But in terms of electricity, it's more about the mechanical work done divided by the electrical energy provided. So that might be more about force times distance of lifting up an object divided by I times V times T of the electricity itself, power times time. Okay? So I just want you guys to understand efficiency still applies here, or I could do this about mechanical power divided by electrical power. Same thing. Okay, in that case, it would just be divided by T, and you wouldn't even care about that T as well. That's basics for circuits. If you understand the relationship between current, resistance, voltage, length, area, you've got a good number of questions covered already. The harder questions are when we talk about series and parallel. Should I jump straight into combined series and parallel, or? Well, you guys hopefully know the basics of series, right? Fine, I'll go over. Series resistors. Basic rules. I is the same, but in parallel resistors, V is the same. Okay, understanding that, and also with series resistors, you guys understand that the total resistance is simply R1 plus R2, etc., etc. On parallel, the total resistance parallel is equal to 1 over R plus 1 over R. Okay. That's just the very, very basic rules. And just understanding that, you should be able to solve for any series and parallel circuit. Luckily, they don't give you anything for series and parallel that's really that difficult. It's usually never beyond 2 steps.
Series is the one that's 1 over. Series is.
For series capacitors, you have 1 over C plus 1 over C plus 1 over C. Parallel capacitors, you add them up. But right now we're doing resistors.
Okay.
So combine series and parallel. Honestly, should we just do a problem? I feel like there's not even that much to talk about.
There are no problems.
Okay, we'll do a problem then. Let me pick one. Otherwise, I feel like I'm just giving rules that you guys don't even care about or listen to. Just pick this one. All right, sketch this.
Oh, you're allergic to nothing.
Parallel.
I went there once.
Why am I thinking about that?
Yes. Because of 4 hours.
Popped out of
And
this.
they wanted us to leave to the table, a bigger party, and we didn't even get dessert yet. Oh, yeah. I don't know, worst experience ever.
My parents went.
For like this one back.
Where did they come
I didn't fall this one. Roll that back.
and they got service like right away.
Then
Some people do it, there's some people who
why
do
don't you
it
just
like
tell
us.
Sherry that
No, I made him.
But they were the ones that were kids there. So they had to like
We were all
crayons.
full of teenagers. How many exams I was in Louise and how my girl was going? And it was weird, she's like, I don't have gas to drive you around, so she jumped us all.
Oh, I would, this was a weekday,
Oh,
I
was
would
it?
be in the college staring at the clock.
Oh, that's when we went to, oh yeah, I remember when we went to.
This
Oh,
is-
that's
this
when we
is
went
the
to,
time I first started.
yeah, but that was for Fridays.
Okay. So, if you copy this down,
Yeah, I got it.
the question is, which resistors you combine first? Okay? You always have to say which resistors you combine first. So, I'll label them R1, 2, 3, 4. Okay. You always want to pick whatever is isolated from everything else. And you have to say to yourself, is it series or is it parallel? Now, if you want to think about this in terms of current, you guys can imagine the current comes out of the battery. It reaches that point, it splits up. Some goes here, some goes here. Some goes down, they combine back together, and it goes back in. Which light bulb is the brightest? Which light bulb is probably the brightest? Christina?
R1.
Why R1?
This is closest to the battery thing.
Okay, that's a terrible explanation. It is the closest, but that's not why it's the brightest.
Okay.
Why is it the brightest? Maria?
Receiving the most voltage.
Not just voltage, though it probably is receiving the most voltage. You're right about that. But it's also, Giordani?
Receiving the most current.
It's receiving the most current. How do you know it's receiving the most current, Giordani?
Because it's closest to
Don't say closest to the battery. That's a stupid explanation. Hamza?
Because the 6 ohm is in series with everything else, and that's the first one in series.
That's slightly better. So in this case, this is in series with everything else, meaning it gets all the current. Before the current splits, it gets all the current. And it probably has the most voltage as well. In the end, so it's the brightest bulb. Now, notice, look at how it's split. One went down, and one went across, like here. Is R1 in series with only R3? No, because the current split. If it's in series by itself, the current won't split. Is R2 only in parallel with R4?
Yeah.
No, because it did split, and parallel means that you have two separate branches, but this current went through how many resistors? Two. So R2 is not in parallel with R4, it's in parallel with 3 and 4. So ultimately, the only one that's really not affected by anything else, 3 and 4, what kind of circuit is that? Because they're on the same current loop. Okay? So that's the one I'll combine together first, 3 and 4. And how do you combine resistors in series? I just add. So 6 ohms, 4 ohms, 10 plus 2, 12 ohms. Okay. So now I have R1, R2, and R34. What's next? Okay. I still have current coming out of the battery. All of it goes to R1. It splits into two separate branch current loops before it come back together and they go in. What do I combine next? Hamza?
The 4 and 12 ohms in parallel.
Right, 4 and the so R2 and R34 are parallel to each other, separate current loops. And you're right, you combine them by doing 1 over. So 1 over 4 plus 1 over 12, which is really 3 over 12, which equals 4 over 12, which means that the total resistance of R234 is 3 ohms. Yes?
Why don't you combine 6 and 4 first?
Well, because they're in series with each other?
Yeah.
But series means they have to be on the same current loop, right?
Yeah, yes.
So look at how I drew it. When the current came in,
They have to be having the same exact current,
yes,
and you have to get it to that point where they will get it.
exactly. So you can see now, you see how 3 and 4, they're on the same current? So 3 and 4 have to have the same current. But 1 won't have the same current as 34 because it's split off.
Yeah.
That makes sense?
Yes.
Okay. So that's why I combine 2 and 34 first in parallel. Now if I redraw it again, I have the 6 ohm resistor, the 234 ohm resistor, that's 3 ohms, R1, R234. If I think about the current going all the way around, I can see they're all on the same current loop, so therefore it is a series circuit. But now I leave it, okay? And now this is when I start making my chart. Whenever I get it to a basic series of basic parallel, my final total will be the summation of this. So I now make my RVIP chart. One, 2, 3, 4. I combine 3 and 4. I combine 2, 3, and 4. And then the total, which is, in this case, the total is a series circuit. So the battery, I'm going to say. So now in the final one, I have a series circuit combined. And with the final one, it's really combining 234 with 1. Okay? and that creates the battery. So in this case, I'm only looking at this very last one. 1 and 234 is 6 ohms, 3 ohms. And you can see that overall, the total, of course, is 9 ohms. Now, with the 9 ohms there, I know that the voltage of the battery was 72 volts. Maybe I should do it like this now. I don't actually fill in the rest of the chart yet. So now, with the 72 ohms, what's the current? Come on, V equals IR.
72 divided by 9.
Which is?
8.
Okay. And because this is a series circuit, I know that current. There's an I in series, right? It's a stupid way to remember it, but whatever. Okay. So 8 amps, 8 amps. Now because of V equals IR, P equals VI, I know that this is 48 volts. This is 24 volts, and notice they add up. My total power for the first light bulb is 48 times 8. 300 and something. I'm just seeing lazy now. 84. Thank you. Okay, well, total power would be 72 times 8, which is 576. Okay. How is that, guys?
Not bad.
Not bad? It might work better if you guys leave the rest of it blank first, and you only do the ones of the last one. Now let's work backwards. So we go from here to here. I know that, in fact, if you're working backwards, watch, this might help you. Let me draw a box. Let's draw a box here that just covers this last one. Okay, I just drew a box without anything inside it. Let me delete that.
Just color it in.
Fine, I'll just color it in. No, I'll use another highlighter. It's fine.
Crayon.
Sure, crayon. Why not? So now I'm gonna cross this out.
Oh, no. Crayon's not gonna work.
Okay. So I kind of crossed it out now. Okay. I know, it looks terrible. But if you think about it this way, okay? Before that bottom one was the total, right? You guys okay with that? Now think of 2. So now what we're going to say is 2 and 34. This is the total over here for 2 and 34. So for 2 and 34, I know that you have 4 ohms. And 34 was 12 ohms. And you can see the 4 plus 12, you guys got 3, correct? And what kind of circuit is 234 really? It's a parallel. So we write down parallel here. Now, in a parallel circuit, what stays the same? Voltage. So I know that V, that's 24 volts. 24 volts. I equals V divided by R, you get 6 amps, 2 amps. P equals V times I, 144 watts over there. How is that? Good? Okay, so now, we filled out what we could for 2 and 34. I take this, I cross this out. This is my new total now. I know 3 and 4, when combined together, is really a series circuit. So I'm going to write that down in my series. Now, in a series circuit, what stays the same? This is a total now, right? What stays the same? Well, 3 and 4, sorry, were 4 and 12. No, they did it right? No, 2 and 12. 2 and 10. 2 ohms, 10 ohms. So 2 plus 10 equals 12. And in a series circuit, what stays the same? So that means that's 2 amps, this is 2 amps, this is 2 amps. V equals I times R, 4 volts, 20 volts, 8 watts, 40 watts. And in the end, I can cross that out again now. I get 1, 2, 3, 4, plus my complete one for the battery. I don't know if that organizing it that way made it a little easier or not. Maybe, maybe not. But hopefully, I just want you guys to understand, the whole trick is to use each previous one as the total for the other ones that are combined together. Okay? So before, with the highlighted ones, we combined 1 and 234 to get the total battery. Is that my child?
Yes. Hi, child.
Say hi, everybody.
Hi, Blueberry.
You're a legend in these streets, Blueberry. Remember me?
Did you have the play date?
Do you want a high five?
High five. Your favorite.
Okay.
Say hi, everybody.
Hi.
Voice.
Hey, Feynman, tell me.
Anyway.
Oh.
Remember?
Oh.
Okay. All right. Danny's almost done with work. All right. So, and everything I said is true for capacitors also. But you guys just have to understand that the formulas of capacitors are just slightly different. Okay. For capacitors, okay, instead of using V equals IR, you have C equals to Q over V.
I'm coughing in the elbow.
Good job copying an elbow. Good job. Okay. All right. And instead of P equals VI, we have the formula UC equals to 1/2 QV. Okay. Otherwise, the rules are basically the same. I mean, you have to understand the difference between capacitors and resistors. But otherwise, for capacitors in series, you do 1 over. While capacitors in parallel, you add them up. Hi, Aiden. Parallel capacitors still have voltage is the same, V is the same. Hi, pretty girl. While in series, we don't have current anymore because the current stopped flowing. Rather, we have charge. So Q is the same at all locations. Okay? So if we were to do this, let me just give you guys one more practice question. And we're just going to turn it into a combined capacitor question instead of combined resistors question. So keeping that in mind, let's do... Right. Okay, guys. Shh. Do this diagram. Instead of R, just make it C, 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 and C. Okay? We'll make it... Oh, you found a bagel. Hmm. Okay, we'll make it 10 microfarads, 10 microfarads, 20 microfarads, 20 microfarads. Okay? We'll make the battery 12 volts and combine. You only have to combine one time in this case. Think about which one to combine first.
Wait. Is there capacitors?
These are capacitors. You're welcome, pretty girl. Is the bagel yummy? Can I give it Aiden?
Yeah.
I know. Thanks.
What's so funny?
I'm sorry.
Okay. So in this case, guys, so which capacitors are you guys going to combine together first? Just to make sure we're okay with this. Which capacitors are you guys going to combine together first? Nick? The 220s. Now, overall, what kind of circuit is this? It's parallel, okay. So now, they combine into one. So, this is 10, 10. What's that capacitance now?
40.
40, good. And you guys can see, do we need to simplify anymore? No, because this is already a basic series capacitor circuit now. Okay? So in this case, if you want to go further, we could go further with a CQV chart. But for now, I'll just ask you guys, what's the total capacitance here? So 1 over 10 is 1 over 10 plus 1 over 40 equals to 9 over 40, correct? It ends up being 40 over 9.
Wait, so in a series for a capacitor, you go 1 over to add them, but then for a parallel, you just add them.
Right. Q is the same in all three capacitors, because Q stays the same now, not voltage. Well, so not current, I mean. Q stays the same. While the 220s have the same voltage, split evenly between them. Okay? Any questions? Hopefully I covered a lot of stuff. You guys can email me with questions. I'll try to answer them. I recommend if you guys want to study together, you guys do like a Google Hangout. You can get up to 10 people on a video chat together just to help each other out if you want to try.
We'll be like outside hanging out in the lobby.
Anyway, or if you guys are sick of studying physics, that's fine also.
No.